Okay, so that's the recording starting. So the talks will be recorded and posted. I've had a lot of requests for them already, so hopefully that'll be fine. Uh, of course, Slack has some finite lifetime nowadays. Uh, so this is just a temporary Slack for this meeting. So what were the purposes when it was suggested that STARS Milky Way local volume organize a meeting like this? Well, of course, we'd like to raise the profile of LSST for the Ultracool Dwarf community because it really is coming soon. So it's not, the type of thing that's 10 years away anymore. It's very close. Um, and of course, second thing is that I think it's nice to have a brown dwarf meeting where we talk science. Regardless of the excuse. Um, I would also hope that we could give some serious thinking in this meeting and perhaps in the discussions and breakouts, if we can manage to run them, to discussing what the community needs to do to prepare for LSST. Many working groups and science collaborations in recent years have published roadmaps of the kind of science that they want to accomplish collaboratively and the types of things they want to accomplish beforehand. As soon as you start thinking about that, you think about data, you think about telescope follow-up, you think of archives, um, software simulations, what's going to happen in commissioning, et cetera, et cetera, et cetera. We have some talks on some of those topics. So, thank you, particularly to Kelly Cruz, who volunteered to talk about, her new archive of brown dwarf spectra. And Trent Dupuy is going to talk about the ultracool sheet. Uh, and other talks. And then finally, this is entirely optional, of course, but I hope you will think about joining the official STARS Milky Way and local volume collaboration, and more specifically, the Solar Neighborhood Working Group. Solar Neighborhood doesn't have a very clear definition, but maybe was always meant to mean sort of stars within 200 parsecs. And of course, those are either the stars are mostly in Gaia or saturated in LSST, but the brown dwarfs are not. And so it sort of could also have been called a brown dwarf and white dwarf working group. Okay, so I thought since we have a few minutes and because some of the introductory talks due to people's conflicts had to be moved back, uh, I thought I'd give you my, 3-slide overview of LSST or something like that, just for those of you who haven't really followed it at all. So you can sort of imagine you have time on a 6.5 meter class telescope. LSST is an 8-meter telescope, but it has the equivalent collecting area of a 6.5-meter telescope. And of course, you decide to take, let's say, a 30-second exposure, or maybe more accurately, a pair of 15-second exposures to eliminate satellite trails and meteor streaks and so forth. And if you do that, then you get to 24th magnitude in R band in your single exposure at 5 sigma. Although, of course, you're saturated at 14.6, more or less. You can imagine, just to have in mind the kind of thing that you're doing, if you took about 800 exposures then, or 800 times 2 times 15, then you're exposing for 6-7 hours. So it's sort of one night of observing time. And so, of course, you could do that if you like on your favorite object right now, right? My favorite object's at 1207, 33.4. Right, minus 39, 32, 54. So I could write it right to attack and get a 6-7 hour observation on my favorite object. So we can all do that technologically. It's not beyond the scope of anything that exists now. We'll see what the magic is in the next slide. Of course, you don't do all 6 hours in R band. You split it among the filters, and so one representative filter mix is shown here on my slide. And so you do R and I, Z and Y, and a little bit in U and G. And so you sort of reach of order 26th magnitude AB in most of these bands. So it's obviously quite exciting. The magic then, oh, and just if you don't know what these filters are, they kind of look like this. So from our brown dwarf point of view, the existence of the Z and the Y filters are quite exciting, right? You really are going out to 1 micron. And then of course there are these blue filters that won't be as sensitive to brown dwarfs. What's the magic? Well, first of all, the magic is this: you have a telescope that has a field of view of almost 10 square degrees. And so once you think this through, you realize you could do your project of observing not just your favorite point on the sky, but sort of 20,000 square degrees on the sky, in sort of between 6 and 10 years, depending on whether or not you decide to count overhead and repairs and you do some other projects along the way. So basically, you can see that a 10-year survey can look at, approximately half the sky. And of course, the other part of the magic that rose us to the top of the 2010 US Decadal Survey for astronomy is you distribute these 30-second visits throughout the 10 years. So rather than doing, point by point, what you're going to do is you're going to reach the final co-added depth after 10 years. And by dividing this up over time, now we've opened up the time domain, and so you can observe transients, you can observe variability, you can measure proper motions, which is a key requirement of the project, and you can measure parallaxes for at least things that are both faint and nearby and sort of beyond the Gaia limit. And so that's an exciting aspect of LSST, which of course takes many years of data. And then just to wrap it up, this is sort of a current type of map of what the sky looks like. It will probably be adjusted once more. But basically, you can see that on the right is the one is galactic coordinates, and this one, of course, is sky coordinates. And so you see we're doing the southern hemisphere, high galactic latitudes, low extinction to make the extragalactic community happy. We have some data in the plane of the galaxy, in the south celestial pole, and the north ecliptic plane to much less depth. And then certain areas of the galactic plane we do cover in full depth. So that's the idea. And I have used my time, but basically there are huge numbers of simulations out there. And so you can sort of see that in Z-band, in this particular survey, you can see you're pretty uniform in the high galactic sky, and you really are, at around 25.6 magnitudes for your 5 sigma depth. Okay. Are there any questions before we move on with the actual presentations about how to proceed? Peregrine, are you here? Oh, okay. I have one more thing to say because I see some uh, dots here. Uh, Peregrine, are you here? I can't see everyone. Well, I don't see Peregrine. Well, we're all doing this on a volunteer basis, so it's a little tricky. Will, maybe you want to go ahead and maybe you could just give your talk now if Peregrine is late.
I can. I'm ready and willing.
Let's do that. Uh, yeah, let's do that.
Okay. Um, Need you to unshare, please.
Oh, yeah, sorry.
Yep. All right. How does that look?
That looks great.
Okay, good. And this isn't quite the overview talk, I'm sure you imagined. But I will be summarizing some things about ultra-cool studies in general. So, hi, everyone. I'm Will Best. I'm a researcher at UT Austin. I study brown dwarf populations, how they form and evolve in various places, including in the solar neighborhood. So as we get into everything that LSST is going to do for us, there we go. Let's remember that brown dwarf science is what it is today because of these large wide field sky surveys. Most brown dwarfs were discovered with surveys like this. They also provided most of the photometry and astrometry that we use. So they have driven the field, and we expect LSST is going to drive it much farther forward. But it makes sense to look back at its most similar predecessor, which was the Pan-STARRS 3Pi survey, and see what we can learn from that. So Pan-STARRS, the 3Pi survey was also optical, didn't have a U filter, but that doesn't matter for us. The red end is what mattered so much for ultra-cool studies. And in particular, that Y band was crucial for identifying and characterizing LT transition dwarfs. The Y band colors, in particular, combination with Y's filters, was able to distinguish these late L and early T dwarfs from background M dwarfs much more efficiently than near infrared colors could. My search in 2015 found 80 of these objects, almost 30 of them within 25 parsecs, and this really helped complete the census of, I think, a missing spectral type range. You're able to complete the census within the local volume. And LSST, based on the numbers you just shared, John, is going to go some 4 magnitudes deeper, so greatly expand our census for brown dwarfs in general, and LSST in particular, I expect will contribute with the LT transition. Pan-STARRS was also a multi-epoch survey over about 4 years with a complicated cadence trying to satisfy many different science goals. But Pan-STARRS produced really useful proper motions and parallaxes. We know in particular that Pan-STARRS was able to find parallaxes for mid-L dwarfs out to 30 or 35 parsecs. That's beyond what Gaia is able to do. And of course, LSST is going to go much, much deeper with these red objects. So for population studies, the gold standard is complete volume limited samples. And a lot of surveys and projects contributed to these samples, Pan-STARRS in particular, through the LT transition. My 25 parsec sample just published the latest paper on it, has more than 500 LT and Y dwarfs, parallaxes for nearly 90% of the members, and a lot of photometry from which we've been able to calculate bolometric luminosities. Of course, there's also the all-sky sample, 20 parsecs by Kirkpatrick et al., who have a new paper out, and he's talking shortly, so I'm sure he'll tell you all about this. What could these samples do for us? Well, they reveal population characteristics that you don't see with incomplete samples. In particular, in the LT transition, there is this gap that we identified in color magnitude diagrams. As L dwarfs cool down and evolve, they move down this plot and then become bluer as they become T dwarfs, and evolve bluer across this track. And there's a gap there that must be a rapid phase of evolution that hasn't really been explained yet, but we're only able to identify because our sample is complete in the LT transition. Another major goal of these volume limited sample analyses is to constrain the mass and age distributions and shed light on the formation history of these objects. So we know star formation produces objects with a characteristic mass distribution, which we call the IMF, initial mass function. That distribution is well characterized for stars, higher mass stars, but still poorly constrained at the low mass end. But we know brown dwarfs do not lose mass as they age. So for a sample, if the sample is remained the same, the mass distribution now should be the same as the IMF. And it's often characterized as a power law, and that alpha for the low mass end has been a major goal for a long time. And the other goal is the age distribution, which is often parameterized with an exponential, and beta is the exponent. If beta is 0, that means you have a flat age distribution. But these things are hard to determine because brown dwarfs have the well-known mass age luminosity degeneracy. We can't tell how old they are just by observing their luminosity. And they've been forming for 10 billion years, so we have a mix of ages in the local volume. We need something else in order to back out these parameters. What we do is we build synthetic populations using these parameters, find observables in our synthetic populations, and compare them to our actual observables. So to date, results for alpha for the IMF, first of all, looking at the comparison sample of star forming regions, there's been lots of work, many more I'm not showing here. This is just a sample, but they've generally found values of alpha between 0.5 and 0.8. Positive alpha means more objects toward the low mass end. In the solar neighborhood, many results in the last decade or two have found something different. They found a negative value of alpha. So this has been in tension. And this was a motivation for our work. There is, at the bottom of that second table, recent work that was concurrent by Kirkpatrick et al. Found a different result, a positive alpha, and we'll get back to that. Summary of the age distribution results looks different. There's been very, very little, actually. Their samples just haven't been sufficient until recently to offer a good constraint. Day-Jones et al. Were able to offer that beta couldn't be too positive, less than roughly 0.5, but there's really nothing else that's a real constraint in the literature. In fact, what's most commonly happened is there's just been an assumption that the age distribution is flat, and how many times have you seen a statement like this? Well, we didn't want to do that, so we built an analysis to constrain both the mass and the age distributions. We determined the luminosity, bolometric luminosity function for our sample and for all of our synthetic populations based on different values of alpha and beta. And we compare them. What can we learn from this comparison? Well, the luminosity function can partially constrain the mass and age distributions. There's a clear trend here, but in particular with beta, the plausible fits actually extend to unrealistically negative values. We really don't have a good constraint on one side of beta. We need something else to really understand what the age distribution is. And we have found a second constraint, an orthogonal one, in the number of young L dwarfs in our sample. L dwarfs in particular, you can identify when they're younger than roughly 200 million years with low gravity spectroscopic signatures or young moving group membership. So we determined the fraction of young L dwarfs in our sample and also in all our synthetic populations. And that's the distribution that you see here. And when we put the contours on the same plot, we see that they're orthogonal to each other. They go different directions. Combining them gives us a very nice joint constraint simultaneously on both alpha and beta. These are the best constraints to date. So what are our actual results? Well, again, comparing to star-forming regions, alpha has been usually found to be between 0.5 and 0.8. And that is right where our result lands as well, 0.58. So we've resolved the tension with other results by finding that we do have an increase in the number of objects toward lower masses, presumably with a cutoff at some lowest mass. So we now are also apparently consistent with the result of Kirkpatrick et al. But there is a difference in our studies in that we do not assume an age distribution. Instead, we have solved for one now. And our beta that we come up with is negative 0.44 based on our analysis. And it's more than 3 sigma away from beta equals 0. So we're strongly claiming that the sample is preferentially young, and we should not be assuming a uniform age distribution. and demonstrated that that's not valid. You can see it on our contour plot as well. That's where the uniform age distribution lies on our plot. Our result is more than 3 sigma away from it. We need to move away from making that assumption. And we have the data now to actually fit for an age distribution. And LSST, of course, is going to greatly improve that. But I want to point out that this young age distribution is actually something we should be expecting. First of all, Dupuy and Liu found a similar thing looking at dynamical masses of binaries. In their sample, they found an age distribution very similar to ours with a median age of 1.3 gigayears. And they pointed out that this makes sense because of dynamical heating in our galaxy. As objects in the midplane, like our volume-limited sample, orbit the galaxy, there's gravitational interactions with clouds and other objects, and this excites objects away from the midplane over time. So older objects should preferentially have been scattered away, leaving a sample that's biased towards younger objects. And this brings us to a really crucial point, which is that the age distribution of ultracool dwarfs that we observe in our 25 parsec sample does not directly reflect the historical birth rate. And there is also the effect of galactic dynamics mixed in. We have to account for galactic evolution in our analysis. And this is new for our studies, which have focused only on the midplane, where we've been able to assume a homogeneous distribution of objects in a small bubble. As we go to LSST, we're not going to be able to make assumptions like that anymore. But LSST will be able to help us with that. It will greatly expand our parallax-defined volume-limited samples. Numbers that John just showed show the sample going 4 magnitudes deeper. If that holds up, we'll be expanding our volumes of our samples by 150, let's say. It'll be much, much larger samples now. We'll have L dwarfs out to hundreds of parsecs, T dwarfs to greater than 50, maybe 100 parsecs with parallaxes and good photometry to characterize them. But we will now have to account for galactic structure, galactic dynamics, how things have changed over time. I know we're going to hear some talks about that at this conference. But LSST will be able to provide us the samples with parallaxes for many of these objects to map these populations and shed light on the ages and how they have evolved. So we're going to have to deal with more complexity than we have before, but we will have the data to do it. So quickly summarizing, pan-stars, which is the most common, most like LSST of the previous surveys, was a vital contributor to completing volume-limited samples, especially in the LT transition, and LSST will greatly expand that. We already have the data to get constraints on both mass and age distributions, and we've been able to show that the age distribution in the solar neighborhood is not flat, but this is really going to expand into multiple galactic populations and structures, and LSST will be able to help us with that. And that's all I have. Thank you.
Excellent. I was so fascinated by this, I didn't check to see if there are any questions yet in the Slack.
I don't see any myself.
I do see a hand raised, however. So, Bhavana, I'm sorry, would you like to go ahead?
Yes. Hi. Well, my name is Bhavna Lalchan, and I have a question about the L-dwarf sample that you have in your that you just now presented. So the solar neighborhood sample that you have, is that within 25 parsec?
It's all within 25 parsecs.
Okay, so so the L-dwarf sample, they are also from the star-forming regions or from how do I say, the field dwarfs, everything together?
There actually are no star-forming regions within 25 parsecs.
Okay.
So there are some L dwarfs from young moving groups.
Okay.
A handful, not a lot.
Okay. So how did you calculate the bolometric luminosity for this study?
Right. So We did this mostly using relations from Filipazzo et al. 2015. Dupuy and Liu 2017 developed polynomials based on those relations that would convert K-band photometry into a bolometric luminosity. So we've done that in most cases. For the very faintest, coldest objects, we used not K-band, but we used mid-infrared photometry from Spitzer or Wise to determine a bolometric luminosity. And there's a lot of detail into that, but it's in the paper.
Yeah, I look forward to read the paper. Thank you so much.
Sure.
Okay, so I think the correct order is Christian has a question about the models you used, and then Brianna afterwards.
Okay.
Hi, great talk. I have my question is like, how much does your result on beta depend on the choice of evolutionary model?
Okay, yeah, good question. And if I can find it here, I have a bonus slide. So I'm glad you asked. There we go. So we use the Soman and Marley 2008 hybrid models for the analysis that I showed you, but Aniket Sanghi was a student of mine here at UT Austin. He's now a grad student at Caltech. Ran the same parallel analysis with the Kahn models, and we found very little difference. You can see there's a bit, but everything is well within uncertainties. We would love to run more models. We found that most of the models out there, the grids weren't wide enough actually to sample all the parameter space we wanted to, but we're looking forward to doing more in the future and seeing how much more effect there might be.
Okay, and we have time for one more question from Brianna.
Thanks. Really interesting stuff. Well, I guess I was wondering, you're talking about the age is affected by the galactic evolution, and how much do you expect that to be affecting the actual mass distribution? Is it going to preferentially remove lower mass things, or
Yeah, hi Brianna, great question. And yeah, we're going to have to account for that too. Although we haven't in this analysis, but if it depends on how masses are being influenced by the galaxy in the dynamical heating scenario. If it's something that you could model with like a nice smooth gravitational potential, like gravitational models often do, then you would expect to remove lower mass objects more efficiently, and that easily could skew the mass distribution. It would actually mean that the original mass distribution had even more low mass objects in it, and alpha would be even more positive. But I actually am not sure, and I have not been able to find an analysis that shows how this actually proceeds. If the dynamical heating is mostly due to giant molecular clouds that treat all brown dwarfs and stars like test particles, then maybe the result is somewhat different. And I think this is an area for future study that's ripe for information.
Loredana?
Yes, thank you. I have a question about the observing strategy. So do you know that the number of visits planned in the galactic plane is smaller than outside the plane? So with the LSST observations, you will have a footprint different. So if you are going to analyze a volume, let's say C times in radii larger than that already analyzed by you, do you think this homogeneity in the number of visits could introduce some bias in the determination of your initial mass function, luminosity function, and so on?
Yes, absolutely. This is something that will be important to account for. This is not something that brown dwarf studies most have accounted for before, the galactic structure, but we will absolutely have to understand the scale height, and again, how dynamical heating has heated objects of different types up into the thick disk and possibly the halo. I think we're going to hear some talks this week where a couple of folks, Christian and Aaron Meisner, have already been looking at objects that are out of the galactic plane. So maybe they'll have something for us.
Okay. Will, if you could turn off your screen sharing.
I have. There we go. Okay.
Okay. And If you don't mind, I would like to just take a moment to acknowledge that, I'm sorry, I'm just trying to show a different slide. I'm happy to say that Shiv Kumar has been able to join us. As many of you may know, 65 years ago, Dr. Kumar, as a postdoc, took on the project of calculating the evolution of very low mass stars below 1/10 of a solar mass. And he discovered what's now known as the hydrogen burning limit, right? That stars on the, I put here just a plot of MESA models, not his models. But you can see that stars that are 0.08 solar masses and higher, settle to a constant core temperature and therefore become main sequence stars. And for lower masses, they fade off. And so this was his discovery, one of the most fundamental in astrophysics, and certainly totally fundamental to everything we're working on today. So I'd like to thank him for tuning in and point out that he didn't just discover this, he realized its significance, right? That there are nearby M dwarfs that we think are stars, but that will turn out to be brown dwarfs. That since this process, as you can see on the horizontal axis, takes 100 million years, star formation doesn't know anything about it. And so he, really did predict and advocate for the view that brown dwarfs must exist, which was quite correct. So I don't know if Dr. Kumar is able to say anything, but he's tuned in on the Zoom, and I'd like to thank him for founding our field.
Hello, John, and everybody else there. Thank you for inviting me to participate in this important workshop. And I'm happy to be here. And I'll be watching you and listening all of you off and on during the meeting. And so keep going. You are doing a good job so far, and keep on doing what you are doing. You are all good astronomers and good scientists. So that's now for now. That's it for now. If
Thank
you
you.
have anybody has any question, you can send me by my email address. And John, you know my addresses, so please give my email addresses to them. But I will be joining you off and on during the meeting. Okay. All right.
Thank you so much.
Hi. Thanks, John, and everybody else for being here and paying attention to pay attention to you other people talking. Just ignore me. Okay. Okay.
Great, thank you. I don't know what's happened to Peregrine, but maybe Davey could go ahead with the next talk.
Sure. I think I am ready.
And I hope you can share your screen.
How's that?
That looks good to me.
Okay, great. All right, well, thank you, everybody. I am Davey Kirkpatrick. I'm an astronomer at IPAC at Caltech. And I've been working in this field so long that when I first started, we didn't have any brown dwarfs to play with. So this is really great to be in this sea of brown dwarfs now that we can study in such detail and get all these great results from. So what I'm going to do, and I would like to thank Will for that great introduction to the IMF that he just gave. I'm going to jump right into the results that we had from my paper, which appeared late last year on AstroPH. And this was building an initial mass function across all masses using the 20 parsec sample, full sky 20 parsec sample. And what I've done on this plot here is just zoomed in on the low mass portion of that IMF that we got. On the left-hand panel here, we're running from 1.5 solar masses down to 0.4 solar masses. On the right-hand panel, we're going from 0.4 solar masses down to 0. What you see as the black points at the error bars there are the number of objects in the 20 parsec sample for each one of those mass bins. And you can think of that as a space density, if you will. And then there's also a fit, a power law fit, and this is a multi-part power law fit to those space density points, which is shown by the orange line. And I want to highlight 3 areas here that I think LSST can potentially help with. Because these are, once I built the IMF, I realized that we've got more work to do here. And these are the ones that I have labeled 1, 2, and 3. One on the far right side are the brown dwarfs, where we need more checks of the theoretical models that go into determining the IMF there, because there, as Will was just saying, you can't determine the masses directly for brown dwarfs. You have to go through some theoretical hocus pocus. What we did for this paper was we looked at the observational effective temperature distribution and then did a bunch of simulations using various forms of alpha, various birth rate functions and things like that to see which of those simulated T effective distributions best fit the empirical one. But we want to make sure that the theory that underlies that is actually sound and is giving other checks along the way. And I'll get to that in just a second. The second point, which is point number 2, which is over in the left-hand panel, is this weird bump that you see in the IMF. And I think that's not real. We'll get to that in a second. And then the third point I want to bring up, which is the bigger one, is all this sort of jitter you see in the space densities themselves. I think all of that is not real either. And I think we have a lot of cleanup that we still need to do there. And I'll talk about that as the third bullet point. Okay, so the first bullet point is the brown dwarfs. I'm not going to dwell on this too much because there's several other talks later in this workshop that are going to address this. But I'm just showing one example here on the left of checks you can do against the theory and what we're getting back as observational empirical measurements for these brown dwarfs. And this is just showing for various for various temperature bins what the expected distribution of masses would look like in each one of those bins. And those are the 3 different histograms you see there with various low mass cutoffs. And the black data points over each of those histograms is showing you where we have a mass measurement in that bin of something that we actually know the mass of. And you shouldn't see any black points that fall over a part of the histogram that's not populated with anything. And you see there is a problem in the 900 to 1050 Kelvin bin where we've got a couple of objects that lie outside the histogram. So that's something we need to continue to check. It would be nice if Rubin and LSST could give us more such binaries to actually measure masses for. But as I said, other people are going to be covering that later, so I'm not going to dwell on that. But let's go to point number 2. So point number 2 is actually sort of outside the ultracool dwarf realm. This is actually more around the K to M boundary, but I wanted to discuss it here because it relates to point number 3. And what I'm showing here is a zoom in on that left panel that I showed on the first slide. And what we do normally to get masses mapped into spectral types or colors or whatever is to use various relations that people have found over the years. And the tightest relation is the one that Delphos found many years ago, which is if you use a absolute K magnitude, you get the tightest relation against mass. And people have been using basically that paradigm ever since. And there are 2 regions, there are 2 relations that relate absolute K magnitude to mass over this region. One is by Stassen et al. That used detached eclipsing binary systems of the masses of the individual components there to actually build an MK to mass relation. And those are from measurements by Torres et al. And there's another sample, which is by Andrew Mann, which uses Bayesian analysis of objects that have M sin I measurements and does some Bayesian analysis on that to figure out what the most likely values of the actual masses are for the components in those binaries and builds a relation that way. The relation does have some overlap. The 2 relations have overlap in them. So if I just pick a dividing line, and on the left-hand plot, I picked a dividing line at 0.6 and said, okay, here's where I'm going to switch between Stassen and Mann, you see I get this bump. And I thought, well, okay, is that bump there because that's where I put the dividing line between relations? So I decided to slide it back to about 0.73 solar masses. And you see the bump goes away, but now I have a new bump on the left-hand side. So the 2 things aren't agreeing. And the 2 things may not be agreeing for one of 2 reasons, or possibly a mixture of both. One is we don't have enough attached eclipsing binary systems, so the Stassen relation is maybe a little too data starved. Or if we look at the Mann relation, it could be that maybe some of the Bayesian priors that go into that aren't quite right. So we're not getting exactly the right individual masses out for those. So I think the solution to this is we'd like more detached eclipsing binaries, which are also a double-line spectroscopic binaries, where we can just get the masses directly of both components and not have to worry about this. And I was trying to build this compilation over the weekend, and I probably missed some things here, but I was looking at all of the temporal surveys that have pulled out things that are at least eclipsing binary candidates. And it looks like we're doing pretty well for the number of candidates. And it looks like there are lots of candidates we can now pull out going down to at least early to maybe even mid-M. So I think we'll solve this problem at the upper end, but we would also like to do the same sort of analysis for the later M dwarfs. And I think our best hope at this point for getting things outside of LSST are probably ZTF and Gaia, but I haven't looked at either one of those lists to see exactly how far down they're pushing so far. That's TBD. But one thing I would like to emphasize here is it's really a multi-survey effort to find a sufficient number of late M dwarf eclipsing systems that we can use for this sort of analysis. And one thing I also want to highlight is this paper by Andre from the test data, where he's showing some of this is an example of one of the objects where they see a single eclipsing event and don't see another eclipsing event. So it's objects like this we want to put on an alerting system and a linkage system for LSST to say, okay, if we see a second event in this, and they'll tell us, okay, there's sort of a binary we can study on a human lifetime, perhaps, and let's go after that and try to get it in more detail. So I'd like to see that sort of alert and linkage system actually exist. Third thing is getting back to the later M dwarfs, and that is really the follow-up of the 20 parsec sample is incomplete for characterizing the known components to those M dwarfs, and also known companions to those M dwarfs, and also finding new ones, because there's a lot of M dwarfs that are kind of fresh and haven't been touched yet. And I'm just showing you here one email, and this is just a random M dwarf within 20 parsecs that Catherine Clark at IPAC and I have been going back and forth about. And the question is it a binary? Is it a triple? We think it's a binary from Gaia, but there's another paper that says it might be a third component. And sort of these things that we still need to sort out, because I really would like to have this 20 parsec sample as a fiducial sample where we know as much about it as we possibly can. We can build the most precise IMF that we possibly can based on the field. Here's an example of a new Gaia discovery that's an M dwarf within 20 parsecs that hasn't had much follow-up yet. And it's an example of the kind of thing I think we should think about doing for all of the 20 parsec neighbors, and that is keeping an eye on all of them and having a system where we're actually trying to determine the multiplicities for all the M dwarfs within a 20 parsec sample, paying particular attention to those that have been flagged in Gaia as having high Rui and Lui values. So we think there's probably a possibility, very strong possibility, there's a second or even third components there. And if you do this sort of program to keep an eye on your neighbors and you want to routinely check that all the stars within 20 parsecs, are they varying in any way that could indicate there's a hidden companion there? Are there multiplicity on the images, either a fainter common proper motion companion or elongated images that might indicate a barely resolved binary or astrometric wobble? And the last thing I want to do is just emphasize the role of citizen science, because a lot of this stuff I just talked about on the last slide is really tedious, it's boring, there's a lot of stuff to do. If you want to monitor every star within 20 parsecs, that's 3,600 objects, and that's a lot to have to do. But the citizen scientists are really well equipped to deal with sort of monitoring, because they can cut off the chunk that they're happy with and do that, and another person can cut off another chunk that they're happy with. And I would like to encourage the scientific community to keep citizen science in mind when they're thinking about these big picture questions. And the montage I'm showing here and on the next slide are citizen scientists who are on my last paper and actually helped tremendously in helping me build the 20 parsec census in the first place. And finally, having spent the last 3 years of my life building this 20 parsec census and trying to make it as complete as possible, I would really hate to see it go immediately out of date and not continue to be updated. So I think one of the ways that we could do this is possibly with citizen science also, and actually ask them to do some of the monitoring for us and help us keep this list up to date. Okay, and that's all I've got.
Thank you, Davey. I wanted to ask, because I wasn't sure I understood what all the different points in histogram you showed. You had a lot of black points that had error bars on them for the mass function. So what do those represent? Because obviously, like, point to point, they're not bouncing around by the error bars, right? So they're
okay. So
what is each thing here?
Okay, so the blue, which I didn't go into this, but the blue histogram is the actual number counts bent up in mass for all the objects within 20 parsecs. Each one of those is going to have its own uncertainty in mass, depending upon how well the absolute K magnitude was known, or maybe maybe had to do something other than absolute K magnitude to get the mass estimate out. So what we do is we Monte Carlo all those uncertainties to try to build up the numbers in each bin but letting things float between bins. So you actually get a real uncertainty on the space density, if you will. So those are the black points with the error bars. So there's sort of a histogram with uncertainty on it, if you will.
Excellent. Elliot has a question, I think.
Okay.
Hopefully this is working. So Davey, you mentioned needing more M-dwarf eclipsing binaries, right, for masses. And so my question is, maybe this is really naive, but would a dedicated RV follow-up campaign for test eclipsing binaries address this, or is there some major potential issue with that approach?
No, I was just looking for something that I thought was fairly straightforward and easy to do, which, well, I don't know if it's easy to do, but it's easier for me to think about, which are the the double-lined detached eclipsing binary systems. Yes, you can also use other binaries, and like you say, to get masses as well. I just want to veer away from having to rely on things that have the sign I ambiguity.
That makes sense.
That's it.
Trent?
Yeah, just on the point of the man at all and the Stossen thing. So the man relation is deliberately has that higher mass cutoff in order to avoid post-main sequence evolution. So I was just wondering how when you do go to higher masses, then you have to assume something about the ages or know something about the evolutionary status, right, to be able to assign. I mean, I know there's the Stossen. I guess I don't know how the Stossen relation handles that.
Well, I mean, we're talking well below a solar mass here, so there shouldn't be a lot of evolution. There might be a little bit of, evolution just going down to the zero age main sequencer back up again, but that's pretty minor compared to, evolution off the main sequence entirely. Is that what you're referring to, Trent?
Yeah, I mean, so of course, so on the low mass end, just taking a step back, on the low mass end for the man relation, you have to worry about pre-main sequence, but on the high mass end, 0.75 solar masses was chosen in order to avoid any post-main sequence evolution within a Hubble time, right? But yeah, I mean, obviously, 0.8, you're probably still pretty safe, but somewhere around there, somewhere between 0.75 and 1 solar masses, you do potentially. I guess it depends on how many oldish stars might be in the 20 parsec sample, but.
Mm-hmm. And it's entirely possible too that the Stassen sample may have a little bit of bias in it just from the few stars they had to pick to form the relation. So that is something to be wary of. So point taken.
Davey, what are your thoughts? I mean, the Gaia published, 100 parsec nearby star catalog. And maybe you don't trust the 100, maybe do 80, right? Does that improving the number statistics, is that more important or not so important compared to just the problem that you've raised about how you actually get a mass out of the data?
Well, I think if you wanted to do higher masses, going off the left-hand side of this plot, you certainly need a bigger sample. No doubt about it. But I think that's pretty much been beaten to death as far as I'm concerned, because I assume saltpeter out there anyway, and it looks like it fit just fine.
Yeah.
But if you're talking about, trying to refine the IMF in sort of the late K and M dwarf regime, then I would hate to have to deal with more than 3,600 objects, which is already what the 20 parsec sample is giving you, and studying those in immense detail. I mean, once you start opening that up to, 80 parsecs or 100 parsecs, you're going to be absolutely swamped with the number of objects. And I think it's the point of diminishing returns, having to deal with a larger sample size with its biases that are coming in, and the fact that they're further away and they're harder to study for multiplicity, et cetera, et cetera. So I think a 20 parsec sample is actually comfortably large. It gives you the statistics you need without being overwhelming as far as the number of objects you have to monitor individually goes.
Okay. I just posted a link in the Slack that the Noir Lab people shared with me, for next week, we do have a tutorial for the data access, and you need an account. And so I think that the link I just sent gives some instructions on how to get started on that process. Okay.
You need,
Um,
John, one quick comment is you need LSST data rights to be able to do that. So,
okay. So, okay, so that was Jeff. I don't know who said that, but anyway, yeah, so
That
the
was it.
data rights issue.
Aaron? Aaron
Oh,
Meisler?
Aaron, yeah.
Sorry
Yeah.
about that.
Okay, well, yeah, so for that'll be for, obviously, people in the US and Chile have data rights, and then it's more complicated elsewhere. But in any case, if you can do it, you may be interested in trying to sign up for that now. Is Marina, are you ready to go now?
Yes.
Great. I think you should be able to share the screen.
Uh-huh. Yeah, I guess you can see my slides.
Yes.
Okay. So, hello everyone. I'm Marina, and I'm postdoc at INAF in Italy. And today I'm going to talk about the work that I did during my PhD concerning the study of ultracool dwarfs using the dark energy survey data. So why ultracool dwarfs? And the answer, as you know, is that there is still a lot that we can do and a lot to learn. And we know that currently the census of UCDs is still heterogeneous and shallow. And a way of obtaining homogeneous samples for this new generation of surveys, for instance, is to use photometric selection and classification. So motivated by this and also by the amazing papers that you can find in the literature, we develop a method to select and classify ultracool dwarfs using a combination of DES, VHS, and all-white. So as I said, we have this catalog, this DES, VHS, all-white data with the magnitude cut at Z less than 23. And we want to select LNT dwarfs. So for that, we took from the literature a compilation of known UCDs and also samples of possible contaminants. In this case, I'm listing here M dwarfs and quasars at high redshift. Then we match these catalogs from the literature with our catalog. So the sources would have the bands that we are interested in. So I'm showing here a color diagram for these literature samples, the M dwarfs, the quasars, and the UCDs. And the dashed line, the black dashed line is our color selection, the color selection that we did. Also, here it's possible to notice that we are allowing some contamination by M dwarfs, but this will be later. Also, using these samples of UCDs and M dwarfs, we construct some color templates for all the colors available in our catalog. Here I'm showing is illustrated here in this figure the colors as a function of spectral type for everything available. And for the M dwarfs, as they were numerous, we basically calculating a median color for each spectral type. But for the L and the T dwarfs, we fit an order polynomial to each color and spectral type relation. So the next step was the classification, where we sort of calculated the spectral type for each source using only photometry, when we call it here a phototype. And we basically implemented the same method as presented in SPRIZIPAC 2015, where the method is consists of a minimization of the chi-square relative to the empirical templates that I show in the previous slide. So here in this plot, I'm showing a comparison between our phototype versus the spectral type from the literature. And the dashed line here represents misclassification by 4 spectral types. And in general, our phototype has an uncertainty of 2 types. We also compare our phototype with other phototypes in the literature, and you can see in the left figure, the results agree really well. So besides the phototype classification, we also decided to use the pair code, LIFAR, to investigate a possible intergalactic contamination in our sample. And LIFAR basically performs a set fitting using galaxy and quasars templates. And we kept in our sample only the candidates which the chi-square for our classification code is smaller than the key from the LIFAR. We also decided to check on proper motions as well, and for that we used these 2 catalogs. And the idea here was basically check if the source has a proper motion different from 0, and to see if there is still some contamination even before using LIFAR. So here I'm showing the final candidate sample, which has a total of nearly 20,000 LNT candidates. And in the left plot, I'm just showing a distribution of photometric distances as a function of phototype. And you can see that our candidates reach distances up to 600 parsecs, which is kind of cool. And in the right plot, I'm just showing a color magnitude plot for the overall sample. We also obtained some spectra from using GMOS from 12 candidates in our sample, and all 12 were confirmed as UCDs with an uncertainty of 2 types as expected. You can see the spectra in the right panel. The spectra is in blue and the best template is in orange. And you can view this as a basic sanity check of our selection and our classification. Also, I'm going to show here some applications that we did to put some use in such an interesting catalog that we have. And I'm going to talk briefly about them. So the first one was the search for white binaries. And we used the candidate sample to search not only for systems with a UCD companion of a star, but also systems composed by 2 UCDs. And our criteria to select these systems was that the pair should have a rejected separation less than 10,000 astronomic units, must have a common distance and our common proper motion when information is available. And in total, we discovered 268 new binary candidates. We also searched for UCD candidate members to young moving groups and associations. And for that, we use the Bunyan code to compute membership probabilities. And we are able to find 20 new candidates. We also search for variable objects using DS variable catalog that we had available. And in total, we found 291 candidates, where 10% are also candidates members to young moving groups and associations. And 1% is in the spectral range of L0 and L8, and 7% is in the L9 and T3 range. Another interesting application that we did was to measure the thin disk KO height for the L dwarfs. And we did that by just comparing the number counts of L dwarfs in our sample with those from the simulation that we have, that is from GauMod. And this KO height was estimated to be in 450%. Just a parenthesis here, I want to say some words about the GauMod because it's a really interesting tool that we have, and would be nice to know. But GauMod is a code that was developed by Basilio, and the code is basically computes predicted numbers of UCD for a given survey, and also creates this synthetic samples of LNT. So this is my last slide. I just put here a summary of the things that I just showed you. And also, I just wanted to say that I hope that my presentation and the things that I said here could be viewed as a model for the LSST. And that's it. Oops, I stopped sharing my.
Great, thank you. Well, we have a question. Maybe I'll start with the question on the Slack from Barbara. Or I can just read it if she needs me to.
Hi, sorry, I didn't know that I had to ask.
I put you on the spot.
That's okay. Hi, Maria, thank you for your talk. When you were showing the color templates, we can see, right, that there is this larger range of colors per spectral type for the M dwarfs. And they get narrow when we go towards the ultracool dwarfs and brown dwarfs. Is that a result that is expected, that the colors are more constrained, or is just that there's not enough numbers to actually see that, you know, diversity of colors?
Yeah, I guess it's the small numbers that we have in this regime. Yes.
And maybe we'll do Trent's question then.
Yeah, I hope I didn't miss it, but I just out of sort of curiosity. So, you know, you're using I, Z, and Y, I guess here, and you know, presumably there'll be far fewer objects detected in I than Z, and in Z than Y. So, have you thought about like the trade-off? Like, is there a sweet spot in terms of sacrificing certain filters to get more objects?
Yeah. Well, we didn't think about that much because we really wanted to use the Y and Z filters from the gas. So yeah, we kind of used everything that was available. Yeah.
Yeah, and I guess you chose not to use R because because for this reason.
Yeah.
And
okay, thanks.
Maybe we'll do Aaron's comment before we do ZJ's question. So because probably Aaron's comment is particularly important for LSST in the future, he commented about deeper W1 data. And so maybe he can
Yeah,
expand
sure.
on that.
I did see that Catwise 2020 was mentioned at some point in this presentation, but I saw also earlier Allwise was mentioned. And to the extent that one is only really interested in W1 and W2 rather than W3 and W4, which I don't know whether that's the case here. But if you are really only interested in W1 and W2, which do tend to be the most relevant for ultracool dwarfs, at least the ones that aren't super nearby, there are now some all-sky reprocessings of WISE and NeoWISE data that go much deeper than all-WISE, like a factor of 2, or in terms of flux. So the ones that come to mind are CatWise 2020, which has proper motions as well, as you mentioned, and then the Unwise catalog, which doesn't have proper motions.
Of course, we're always in the position, we could redo our dissertation, 5 years later in a field. Okay, ZJ.
Hey, Marina, I'm pretty interested in the wide binaries. Do you have idea about the spectral type distribution of the candidate companions that you found?
Sorry, the spectral types
Spectral
for the
type.
stars? For the stars?
For the companions.
No, we didn't check that.
Okay.
Okay, do we have any other questions? So by skipping one talk, we've managed to end up on schedule. So that's that's called excellent meeting management by your host. I think we had a 15-minute break scheduled, and I think that's probably a good idea for us to take it. And then at 1:30, we might hear from Fed Bianco, but if she's not able to get back, because I know that she had some other things, maybe people who are later in the schedule could be prepared to go if necessary. So let's just take a 15-minute break, and thank you. Okay, well, it's 30 after. Maybe we'll try to start close to on time. The next speaker is Federica Bianco, who is, like me, a professor at the University of Delaware. She isn't from the brown dwarf community, but she is very much in the LSST community. And so she's volunteered to give us an overview of the project and maybe its current status.
Perfect. Let me share my slides. Can everybody hear me?
I can hear you.
Okay. Yes, I am not from the brown dwarf community. I'm really not from the stars community at all. Mostly I've done work in transient science, even in solar system, but no stars, so please be patient with me. I'm gonna try, and my slides are loading. I'm gonna try and give you a fair representation of the potential of the survey for stellar science and for brown dwarfs in particular. Mostly this is a high level talk. I have a lot of slides. I kind of see which direction we go. I'll also make the slides available to you, but this is a very high level talk to describe Rubin Observatory, its data, the status of the observatory, and the expectations for stellar science. So my name is Federica Bianco. Indeed, I'm a professor at the University of Delaware in the Department of Physics and Astronomy at the Biden School of Public Policy and Administration and at the Data Science Institute. And as far as Rubin is concerned, I'm Rubin deputy project scientist on the Rubin construction side and interim head of science on the Rubin operations. And I've also been involved with Rubin in a number of roles on the community side. So I'm very familiar with the science collaborations that I imagine most of you are involved with. I was for a long time chair of the Transient and Variable Star Science Collaboration, which works very closely with the Stars Milky Way Local Volume Science Collaboration, and with and I was coordinator of the 8 Science collaboration. So I think I want to start with just reminding you, Rubin Observatory is a joint adventure funded by the National Science Foundation and Department of Energy in the US. It's built in Chile on Cerro Pachón, and the status of the project is that we're in the final phases of construction. And I already have an error in the slides that shows that this slide is old. Completion expected 2023, completion scratch that, expected 2024. We do expect to begin collecting data, sky data this year. I'll show you in a second how we, in fact, are already collecting some sky data and what are the steps to get there. But before I get to that, let me remind you of the 4 science goals that govern the design of the survey and the design of the observatory. So these 4 science pillars, sometimes referred to, of Rubin Observatory, are really chosen to design a facility that is extremely flexible and extremely achieving in different, in very different science topics, and therefore that has the potential to really span a wealth and a breadth of science, of astrophysics, and be transformational in as many areas of astrophysics as possible at the same time. It does start as a survey that is close to cosmology. So one of the science pillars is the probing of dark energy and dark matter, so what we call the dark sector, which Rubin will probe with exquisite measurements of strong, weak lensing, large-scale structure, clusters of galaxies, supernovae, VAO, etc., etc. On the very other side of the spectrum is the very nearby. And so one of the other pillars of Rubin is the construction of a catalog, an unprecedented catalog of solar system objects that will include about 6 million bodies, from near-Earth objects, even threatening in route of collision with the Earth, so life-threatening objects, all the way to the distant or cloud imaging objects that are at the moment too faint to be imaged in a sample. And now we're getting closer to the science that might interest you. This is the science that interests me, the exploring the transient variable universe. Rubin will do so with 10 million alerts every night, which are shared worldwide. This is the world public data product. I'll talk more about the alerts later on. And really at the heart of what you do, the mapping of the Milky Way and local volume via resolved stellar population. Rubin will characterize 17 billion stars in shape, color variability, location, and motion. To achieve that, one of the really critical aspects is the production of an enormously large data set. Rubin will observe for 10 years, and it will collect 20 terabytes of data every night of those 10 years. So that's about 60 petabytes of data over the life of the survey, 3,200 megapixel images over the course of the lifetime of the survey. To achieve that, we built a telescope that has a very high sensitivity system. So it's an 8-meter telescope. Really, it's 6.7 effective collective area because of the very large hole in the center of the mirror, which hosts a very large camera. So we have a very large field of view combined with a high spatial resolution, a sub-second spatial resolution, which will be scene limited, which enables what we call a very large attendu. So essentially the product of the resolution by collective areas, just the amount of data that we can take per unit time. The field of view is 10 square degrees roughly, and the images will be produced into catalogs that together between stars and galaxies will collect about 37 billion objects. This is a fun number because it's larger than the number of people in this ever crowded Earth. So for the first time, we'll know about more objects in the sky than there are people on Earth. Some more numbers for you. I'll dig deeper into these numbers, the ones that are more specifically of interest to you, or that I think might be more specifically of interest to you. But roughly speaking, just to get a sense of it, the standard visits depth will hover 24 And there will be about 1,000, just short of 1,000 visits per area of the sky over the 10-year survey in 6 photometric bands, U, G, R, I, Z, Y, so from ultraviolet to near infrared. And the total footprint will be in excess of 18,000 square degrees of sky, which for all intents and purposes means it will cover the entire southern hemisphere. Roughly what this sums up to is, like I said, about 800 and some images in over 6 filters for every position in the sky, and every position in the sky is imaged 2, sometimes 3 times within a night, and then reobserved within a few days. Let me dig a little deeper into the number as I give you a sense of how the images will look. So what you see is a transition between how an SD. Yes.
Your audio is a little garbled, like it's mostly working, but it kind of.
Okay. Let me remove my earbuds. Is it better if I go through the microphone?
Yes, I think so.
Okay. So what you saw, let me see if I can play it again, was a transition between an SDSS image and an image as it will look for LSST as produced with Supreme Cam images, so HSC images. At this level of depth and resolution and sensitivity, everything is variable, everything is blended, and everything is moving, which obviously adds complications to the reduction of the LSST data, and we do need to build and deliver new reduction platforms and reduction models because of the complexity of the data. So the numbers that I didn't want to dwell too much on the numbers for the depth as you saw them earlier, but I'm going to give you some numbers here with the caveat that the first 4 numbers in this slide are requirement numbers. So these come from a document called SRD, survey requirement document. You have the link here, ls.st/SRD. And these are the requirement that LSST is committing to deliver at the beginning of the survey, but they are under idealized conditions. So take them with a grain of salt. These are not under realistic conditions. These are bore sight, so pointing at zenith in good seeing condition under idealized weather. The photometric precision under those requirements is 5 millimagnitude, photometric accuracy 10 millimagnitude, astrometric precision 10 milliarc seconds, astrometric accuracy 50 milliarc seconds. The number of visits instead come from simulation. So these are the most our best estimate for how the data will actually look. So you can see the transition between what a requirement translates into in terms of real image quality in this document PSTN 054.lsst.io. And these numbers that I'm quoting here come from some of the most recent simulation. And I'll talk a lot more about this simulation in a few minutes. These are the numbers per filter. You see 6 values because of 6 photometric bands, and you see the depth of a single image, which, like I said, hovers 24th magnitude for G and R band. So the second and third numbers are G band and R band, U, G, R, I, Z, Y. And then the co-added depth gets close to magnitude 27 in those bands. Some more transition for as eye candies. These again are simulated images as they might be expected to be seen by LSST as compared to how they were in SDSS. So the status of the observatory, we're getting there. That's the short version of it. This is an image of the observatory in 2016. Didn't look like much. We had just started. This is an image in 2020, so things were going much, much better. But you may have heard in 2020 something happened and we all had to go home for a forcible reclusion of several months that actually extended to a year. And then in terms of ramping up observatory facilities because of interlocking requirement, the delay extend to longer even than the shutdown or than the pandemic and the shutdown of 1 year. So that did comport several months, maybe 18 months, and at least 18 months as of the last estimate that I had heard of delays. But we are back in business. This is May 2022, and you may notice something very desirable for an observatory. Now the dome doesn't have holes, so it doesn't rain. That's you really don't want to have rain in the observatory. And so in fact, this is an image from the observatory when I believe this image is taken as the telescope mount assembly was being brought into and mounted into the observatory. November 2022, you can see the observatory, the dome opens, and we can start looking up. And in fact, the observatory doesn't only include the Rubin building right here on the left, but also this telescope here, that's Auxtel. It's the auxiliary telescope. Together, Auxtel and Rubin and all the data facilities constitute the observatory. I'll show you something more about Auxtel in a minute. Most of these images I have are from May 2022. There's no, just because they were very good images. We had a great photographer, but progress continues. But as of May 2022, you can see the telescope mount assembly. In this image, telescope mount assembly doesn't have anything in where the mirror should be. You can see through. At the moment, this is mounted with weight loads that correspond to the weight of the mirror. We don't have the mirrors mounted yet, but we're running the telescope mount assembly with simulated weights, and we're testing its capabilities as we speak. In fact, I have a short video that I'm gonna go a little bit further into that shows you the remarkable really slew of these telescopes. This is a massive instrument. The weight is 2 × 10⁵ kilograms. The maximum slew rate is 0.2 radians per second. So we estimate the angular momentum being something of the order of 5 million kilograms per meter square per second. And it does move remarkably smoothly for such a large beast. Hoping that you were impressed, I'm going to move on. The secondary mirror is already coated. The primary and tertiary mirror will be coated and mounted in 2024 on the telescope. Maybe the jewel on the crown of the observatory is the DOE LSST camera, which is the largest camera ever built, 3.2 gigapixels. And this camera the final stages of construction are at slack, and the camera is fully integrated, is going to be fully integrated later this year. It's undergoing the really final stages of testing and will be shipped soon. With the camera come these enormous filters that also are available and will be shipped and mounted on the observatory with the camera. And I'm going to show you the exchange of these filters in a quick video, which I also think is quite amusing. So we have a system that changes the filter rapidly within the night. 5 filters are mounted at a time just because of the geometry of the system, but 6 filters are available. So the U and Y band filters, the filters at the extreme of the spectrum, are swapped on the telescope, on the filter mount with lunation, so bright time versus dark time. So 5 filters are available every night on the system, and images are collected within the night in different filters to get instantaneous colors or semi-instantaneous colors. And I don't know if this image lends, but this is supposed to be quite impressive in showing you how actually uniform the CCD plane is with really very high performing chips all throughout and very small variations in the performance. This is a mapping of the magnitude corrected once you correct for read noise, QE, and vignetting for the U band and Y band filter, so the extreme filters on the filter wheel. And you can read more about this in PSTN 054. But the observatory is actually already working. It's running with LOVE since 2022. LOVE is the LSST Operation Visualization Environment. It runs the Auxtel regularly. Auxtel is the auxiliary telescope, as I mentioned, the second telescope here on the hill, which in operations will collect spectroscopic data to facilitate calibration, but at the moment is serving to test the pipelines that will run on the main telescope. That's the software components and the observatory workflow, the data acquisition pipelines, the calibration, the data analysis, etc., etc. So that's the status of the observatory. If you want to get a little bit more quantitative in terms of when should you expect to, log into the RSP Rubin Science Platform and get some data, some hands-on data, you may want to look at this visualization that Keith Bechtel, who's leading commissioning, has produced. So the flow of these phases of the construction go as follows, marking the first photon as a key date. Roughly 12 weeks later, we'll have system first light. First light, the images will be released to the public. And we'll really have the first photon is the first time that an incident photon really hits the LSST camera through the mirror system. We don't know what the quality of those images will be. In the following 12 weeks, we expect to be producing first light worthy images. After 18 weeks, we expect to start the survey. Each one of these time gaps is to be understood to have some contingency, of course, associated with it. So 18 weeks plus contingency, that's when we start the LSST, the Legacy Survey of Space and Time, which will last 10 years. The data that is collected in the first 6 months of the survey will be processed in the following 6 months to be released roughly at the beginning of year 2 of LSST. So you can expect the first data products, static data products, the first catalogs to be released at this benchmark. And if you tie this with our monthly updated dates, we have a website at ls.st/dates where you can keep up with the current estimate for when these milestones will actually happen. So this was last updated in December, so it's quite fresh, and you can see that the 3-mirror optical system is expected to be ready for testing in July of this year. This is again, this is a date plus contingency to be expected, and the LSST camera ready for on-sky, so first photon in December of 2024. So roughly a year from now is when we're going to be in this point. So late 2024, 2 years from now, the start of the LSST survey, and roughly 3 years from now, that's when you can get hands-on catalog data, although there will be data released nightly during the first year of operation, and I will mention that in a second. So far, so good? Oh my God, it's already quite late. Okay, let me pick up a bit. So the LSST data products. There's 2 types of data products primarily that I want to point your attention to. There's the prompt data products. These are word public data. Those are the alerts for anything that is time varying that I mentioned earlier. These are generally produced by template subtraction. I have a few words about that in a second. And they're produced 60 seconds from shutter closed. They're broadcasted to the world via brokers. So we expect that at least 3 good seeing images are necessary to produce reliable enough alerts. And so the current plan is that during year 1, when we don't have templates for the sky, we will, however, begin producing these templates and producing the alerts associated with any area of the sky that has a template available in the corresponding band, so that in year 1, we'll begin to see these alerts coming up. The alert stream will be incremental, meaning that the area of the sky where templates are available will grow throughout year 1 and will be a low fidelity stream because we will only use 3 images, whereas in later years we'll have more images and we'll be able to select better images to construct the templates. But the most recent estimates, sorry about the arrow in the plot, not sure why there's a static error here. The most recent estimate tell us that if we assume that if it's true that we can produce templates with 3 reasonably good seeing images, so 50th percentile or less, in the first few months, though this is 1 year after the beginning of the survey, and this is days from the beginning of the survey. So in the first 3 months, we'll already have somewhere between 60% and 80% of the sky available with templates in most bands. And within 1 year, we should have templates for the majority of the sky. So you should expect to receive alerts, even though they won't be full fidelity in year 1, and a growing amount of alerts because a growing area of the sky will be patched with templates. These alerts are received through brokers. So the workflow works as Rubin is a discovery engine, produces 10 million alerts per night once we are fully templated in the sky. And those get picked up by community brokers, Antares, Alerce, Fink, Glacier, etc., etc. You can use target of observation managers, perhaps, to set up your follow-up observations and Aeon system to integrate your observations and send them to telescope facilities. And ideally, those data will be picked up and sent back through your TOM to the alert system in a fully continuous flow that enriches the information about time domain sky as we go forward, and that enables a very high degree of automation of this process. But this is not a time domain talk, so I'm going to skip over the brokers. But that's, if you're interested in time domain, that's what you should expect to do. If you're not interested in time domain and you want to use catalog level data products, those 17 billion stars that will be observed, catalogs for all of them will be released, which will contain data about their time variability as well as all the other information that you can extract, so color, shape, astrometry, etc., etc. But those data are proprietary. Not that it matters, because for any of you who is at a US institution or Chilean institution, the data is public. And for a number of other communities, there are agreements through in-kind contributions that give you access to data. So it's an enormous data rights holder community, but these data are proprietary for 2 years to this community, and they're accessible through the Rubin Science portal, which will enable access in a variety of ways with APIs, notebooks, graphical interfaces, etc., etc. The Rubin Science Platform is this portal, and I want to flag here that the Rubin Science Platform is actually already active with simulated data from the Data Challenge 2 that was released by one of the science collaboration, produced by one of the science collaboration, the desk, as well as now solar system data produced by the Solar System Science collaborations. And not only the Rubin Science Platform is active, but Rubin is actively seeking people to stress test it and use it and learn how to use it and teach us how to develop it. The program is called the Data Preview Delegates Program. And you can join this program. There's already 900 users or delegates that are working on DP0, the Data Preview 0 on the Rubin Science Platform. And I encourage you to keep up with the Rubin Community Science team that organizes meetups and webinars and gatherings for this community and helps you figuring out how you will use the Rubin data once it's available. Let me just give you a few words about survey strategy optimization, and then I'll show you a bunch of slides very rapidly of expected performance. The survey strategy optimization, essentially, this is what I am in charge of as deputy project scientist. It's done through a committee, the Survey Cadence Optimization Committee. And you can imagine that it's a hard job because these nearly 1,000 images that we collect on each position of the sky can be collected in an approximately infinite sequence of permutations. And each one of those will support some science, but hurt some other science. So it's a really difficult balancing exercise that balances priorities, not only among the 4 scientific areas, but even within each of the scientific pillars. Some science would prefer wide versus deep, or regular and persistent versus fast and dense. So this is the job of the Survey Cadence Optimization Committee, which has worked on this in a very iterative process, very closely with the community. So roughly the way it works is we produce simulations of the survey strategy. We started with 14 simulations in 2014 through the OpSim simulator, and now we have hundreds, thousands of simulations, many of which at this point are obsolete, but we now produce hundreds of simulations at every iteration. And then we, the community, is invited to write white papers, submit form responses in a number of ways to interact with us. And it's an iterative process where we make simulation, we ask how they go, we get suggestions about how other things could change, we produce more simulation, we ask you again how it's going, and blah, blah, blah. At this point, we are at version simulations 3.3. And let me just point out some of the, by the way, the work that you do on this optimization of the survey strategy can be submitted to in focus issue of the APJ supplements, and we encourage you to do so. And if you want to know more, feel free to reach out directly to me. I'm missing the plot here, but this is just to show you how profoundly and specifically about the Milky Way and local volume, the footprint, and the footprint as well as the cadence in all of its aspects has changed throughout this process. In 2018, Rubin was designed really poorly if your goal was to do Milky Way science. Really, the footprint was designed primarily for cosmology, with cosmology in mind. And the evolution has been dramatic. So right now you see how much more detail you have in the footprint of the Milky Way and galactic plane, as well as the Magellanic Clouds and the South Celestial Pole. This came through really fine-tuning how the footprint should be with the science collaborations, with the Stars Milky Way Local Volume and Transit and Variable Star Science collaboration. The most recent simulation, let me see if I can go to the next slide. And this has generated really significant improvements in all of the science that we're able to measure. That is Milky Way science. We're able to measure the science if you provide metrics for science. And these are some of the metrics for science that we generally track. The number of white dwarfs, the number of brown dwarfs, the number of stars altogether, number of young stellar objects, proper motion, parallax. Generally, blue is good and red is bad, and time goes from the left to the right, from circa 2018 through today. And you can see how we've gained in nearly all science cases for all of these metrics in the iterative simulations. I think I'm already out of time, surprisingly, because I had about 3 times as many slides. But maybe the last thing I want to say is the most recent simulations have updated the throughput of the system. So if you are caught up, but until like a few months ago, you may want to look into this. We finalized the decision on how to code the mirrors to be silver for all 3 mirrors. The original plan was aluminum, silver, aluminum. And this changes the throughput with significant gains in all photometric bands except U band. So there's a filter balance shift here. We've lost a little bit in U band. We've gained in all the other bands. We've gained survey efficiency of about 20% with this change in throughput. And we are thinking about whether U-band has taken too much of a hit. Can we just put some of that 20% back in U-band, whether by extending the image duration, the duration of the image collection, or by just adding more images in U-band? All this is ongoing process, and we'd love to hear from you about this. And if you have any questions specifically about performance, I can pop to the corresponding slide on, I don't know, rolling, proper motion uncertainty, astrometry. Just let me know what you want to see.
Great, thank you very much. While we wait to see if anyone else has questions, I guess I do know over the last, say, 10 years, there's sometimes been discussion of switching from 2 15-second exposures to 1 30-second exposure. Obviously, you gain in efficiency, but you lose some other things. What's the status of that?
Right, and I can, for context, maybe I can put the saturation limit slides up. So the current plan is that the images until now, the plan has been that the images are collected in 2 snaps of 15 seconds each to be combined directly at the observatory before the release of any data products into a 30-second exposure. So all the data products come from the 30-second exposure. Originally, the plan was to mitigate cosmic rays. If we can prove that cosmic rays can be identified and removed without the 2 images, then we might be able to go to a single 30 seconds exposure that increases the efficiency of the survey by a lot, by something like between 7 and 10%. The decision is pending, first of all, it's pending the viability, which will only be assessed in commissioning with on-sky data. So we won't know whether we can do that until we get that answer from commissioning. Scientifically, it's hard to beat the 10% gain efficiency argument. And we haven't really heard, the SCOC has not really heard any particularly compelling argument as of yet to stick to the 2 times 15 seconds if the 1 times 30 seconds is possible. Not compelling compared to the 7% to 10% increase in efficiency anyways. Obviously, saturation limit will go up. You would lose the visibility in the 15 seconds timescales, but keep in mind that no data products are associated to the 15 seconds timescale. So if that's what you want to work with, you need to reduce the data yourself. So that's one of the reasons why it's hard to make an argument that is particularly compelling for this. My expectation, and I'm speaking somewhat unofficially because it hasn't been fully discussed by the SCOC, is that during year 1, we will not change the survey strategy, whether we move to 1 times 30 seconds or 2 times 15 seconds. And we probably would rather use that additional efficiency, that additional time as contingency for other things that might happen in year 1. But then we can start thinking like, what can I do with the X% more time? Maybe a micro survey, maybe going deeper in some areas of the sky, maybe just more images spread out into all the bands, all the places in the sky, or maybe changing the filter balance. That's all possible.
Do we have any questions? I don't see any hand raised or chat or Slack, but okay. Well, thank you so much, Federica, for
I'm gonna be on and off around, but you can find me here at sometimes throughout the meeting.
excellent. Next on the schedule, we had Eduardo.
Hello, John.
Hello, I see you.
Good. Thanks for this slot. I realize that we are a community that we don't meet so often, but I think you are aging well. So I'm a bit of an outsider to the LST community. And in fact, I don't think I have data rights because the IC is kind of in some negotiation to see if follow up with the GTC could be part of that. But I don't think at the moment that is still finished. So far, I don't think. Actually, I'm going today to tell you more about Euclid because I think there are significant synergies between the Euclid space mission and LST. Can you see my screen? Do you see my screen?
Yes, I can.
Okay, fine. I am an independent legacy scientist in the Euclid Science team appointed by ESA, and also very recently I have become an ESA-appointed community core survey scientist in the Nancy Roman Space Telescope. I'm also the PI of a European Research Council Advanced Grant team. We are constituting the team. Actually, now we have 3 postdoc positions open until the end of this month. You can check the IC webpage. We have an advanced postdoc, Marusa Serhal, and we have some grad students in the team. And we are expecting to grow in the next few years. Euclid is just passing the science verification and soon to start the nominal surveys. It's mainly an ESA space mission, but with some significant NASA participation, mainly providing the near-infrared detectors. It was launched from Cape Canaveral in July 1st, 2023. You can see a picture of that. Well, you know, it's a picture that we took because we were there. It's not the best picture you can find, of course. It's mainly what it has is a wide field space telescope, and is unique in that, being a wide field in space. It's diffraction limit, and it has 2 instruments, a visual imager with a wide passband, and then a near-infrared instrument with slitless Grissom spectroscopy and imaging capabilities in 3 passbands. The schedule is that the commissioning is already passed, and there was also a phase of study of the PSF characterization, and now we are at the end of all these verification and calibration campaigns, and about to start the nominal surveys that will last for almost 6 years. What does Euclid provide? Here you can see some examples of what Euclid gives in one standard cycle. So it has the near-infrared imaging. There is an array of 16 detectors, and it also has the visual array with 36 detectors. The spatial resolution in the visual is about 3 times better than in the near-infrared. And it also has the slitless Grissom spectroscopy. We are, my team is leading one of the first science projects with Euclid. This is called the Early Release Observation Program. And we have target star-forming regions. At the moment, we are working on 4 regions. One of them is pictured here. It's like a twin cluster in Orion. And we have many thousands of sources in this field. You can see here number counts reaching 10 to the 1,000, more than 10 to the 1,000. This is only in one field of view of Euclid, and reaching quite deep to in the infrared to AV magnitude of close to 24, and in the optical getting to almost 26. And we're starting to characterize this data. It's the first science data provided, and we are starting to construct color magnitude diagrams in these regions to check what is the depth that we're getting and what kind of ultra-cool objects we can detect. The Euclid surveys that are going to start soon have a significant overlap with the LST because a good part of those surveys are in the southern hemisphere. You can see here one of the possible surveys, but this was actually work in progress after the launch. The survey plan had to be changed because of the results of the commissioning and the verification of the properties and well, some problems that arise with the stray light and things like that. So the calculations about the solar angle had to be properly characterized. So well, but just to give you a general idea for what the survey looks like. So it's mainly a survey of the extragalactic sky. And at the moment, in 5.84 years, it's planned to cover 13,000, a bit more than 30,000 square degrees. The ultracool dwarfs in the Euclid surveys are going to be detected to quite significant galactic regions, galactocentric distance, and it's going to be possible to probe into Milky Way populations such as the thick disk and the halo. So we are at the beginning of very exciting times for ultracool science. This is going to be a quantum leap in the numbers of objects detected and available for studies and characterization of ultracool dwarfs. In particular, in this example, for L5 type, you can see the jump that is going to happen in this century thanks to Euclid, LST, and so this is going to really take things into a new era of big data science for ultracool dwarfs. We have made some estimates published in a paper led by Enrique Solano in 2021 about the expected numbers of ultracool dwarfs and M dwarfs in imaging in the Euclid survey. Also in spectroscopy, we published some simulations in a paper in Astronomy Astrophysics, indicating that Euclid can provide low resolution near infrared spectra for many thousands of T dwarfs. So far, the results of the spectroscopic calibration data are very good. They are consistent with the requirements. A summary of what we expect from the Euclid surveys at the end of these surveys for ultracool science is that we expect to go to the numbers of substellar objects in the order of magnitude of 1 million, and with about 100,000 spectra, low-resolution spectra. In terms of substellar binaries, we expect to jump to a number of about 10 to the 1,000, and but well, not so many with dynamical masses, but still maybe a factor of 10 more than what we have today. In terms of wide companions to stars, we expect an increase and going to around 1,000. And we also expect to start detecting a significant number of planets around substellar primaries, and also the first, and not only the first, but a significant number of substellar objects in a metal pool in the halo of our galaxy. The synergies with Euclid and LST are very important. We do have a significant overlap in area and wavelength. So it's very powerful to carry out combined multi-wavelength and proper motion searches. Also for binaries, we have complementary approach to the study of binaries and planetary mass objects. And with all this data, we can certainly expect to bridge and extend the studies of the IMF for populations of different age, in different environments, and across a wide range of masses. That's all I have for today. I'm ready for any questions if you have.
I don't know if anyone can hear me. It seems like my screen is frozen.
I hear you.
Yes.
Maybe Eduardo's screen is frozen. Loredana has a question.
Yes, I have a question about the crowding. Did you explore the crowding issue for the Euclid observations in the, for example, in the star-forming regions that you observed?
Yeah, we're doing that. Yeah, thanks for the question. And yeah, we are comparing the effects of doing aperture photometry, PSF photometry. All of this is work in progress. So yeah, certainly it's something that we're doing right now. Yeah. I don't really have any results because I have some kind of inside kind of plots, but we are not finding a very big problem with that, because we have not targeted extremely high density regions. The regions we have done are regions in Orion, but not the Orion Nebula cluster. That was done by James Webb, and I think James Webb there does better than Euclid. So the big advantage of Euclid is the wide area. So we're targeting not so crowded regions for star-forming regions. So we did some region in Taurus and NGC 1333, and some of the regions in Orion that are not as crowded. And other colleague, David Massari, has a ERO program on globular clusters. So that is more of a challenge in terms of crowding, and there we can learn more about the crowding effects. But we don't really have big issues with crowding.
I'll just ask the question in Slack. Are your postdoc positions also posted on the AAS job register?
You know what? I tried to do that, but it seems that even though IC is kind of a sponsoring institution, well, there were some sometimes the IC positions don't get through there, but eventually it went through, and I'm told it's there. I'm told it's finally should be in the job register. Yeah.
Right.
Yeah, but please just drop me an email if anybody's interested. I will be more than happy to point you in the right direction.
Well, that's good. If we get someone a job, this would be a very successful meeting.
Sorry, could you please drop your email address in the Slack channel so that we can contact you?
Oh, yeah. Okay. Good
Thank
idea.
you.
All
Thank
right.
you.
I will do that.
Okay. Do we have any other questions, or we could move to the next talk? It's exciting that you have a head start on LSST. So, right, it looks like you'll have 2 years of data in hand. So the next talk, ZJ, was it ZJ?
Yep. All right, let me share my
Thanks. I know
screen.
that maybe we're running a little late. I know you had a conflict. Hope this is okay.
Yeah, it works. No worries.
Thanks so much.
Can you all see my screen? Okay. All right. Hello, everyone. I'm ZJ. I'm currently a postdoc at UC Santa Cruz. It's really nice to virtually see all of you, and thank you for organizing this online workshop. So today I'm going to talk about the value of large sky surveys and how we can use them to find benchmark brown dwarfs. And by benchmark, I mean the brown dwarfs that are either companions to stars or members of young moving groups. So over the past two, wait a minute, there's, oops. Oh, all right, okay. So over the past 2 years, I think the most exciting thing in astronomy has been the launch of James Webb and all of the exciting science it has been enabled. And here I show my combo of several kind of new James Webb science results. And when we talk about the brown dwarf in particular, I would say like what impressed me the most has been the spectrum of this object, VHS 1256b. So among all of the brown dwarfs, this is the first object that received the panchromatic James Webb spectrum, spanning from like 0.8 to nearly 20 micron. And with this kind of great data quality and like the whole part of the spectrum, it was not observed before from the ground. So it's pretty eye-opening to see all of the features. And this object is actually a brown dwarf orbiting a young star, as we can see from the image. So technically, it's a benchmark brown dwarf. And also, as we can tell from the name, it was identified by Gauze et al. 2015 from the VISTA Hemisphere Survey. So VHS 1256b is a great example of the benchmark brown dwarf that was identified by large sky survey. So now with this kind of great spectrum, we see a lot of wiggles and features, and they're created by like cloud effects and other molecules, metals, and isotopes. So there has been a community-wide interest to look into these features and try to understand the atmosphere composition, formation pathways of these brown dwarfs and planetary mass objects. So the typical way that people use to analyze this spectra has been to use models. So here, let's see like how the state-of-the-art model spectra look like. So what I'm going to show here is the prediction of the emission spectra from several model sets. And they are all generated at the same kind of combination of the physical properties with a TAF at 1300K, log Q of 4 DEX, and solar composition. And let's see how the spectrum look like. So this is BD Saddle model, and this is NOR Demobat. The blue is Exoram, and green is Atmo. And remember that the y-axis here, the flux is in the log scale. So what we see here is really kind of a large kind of distinct difference among all of the model predictions. So basically this comparison tells us like our understanding of the brown dwarfs and planetary mass objects is pretty model dependent. So to move forward, we really want to have some kind of empirical standards that can maybe tell us like what should the spectrum look like at a given combination of the physical properties, so that like we can use them to sort of calibrate the prediction of the models and try to move forward and improve the model prediction. And if we have a larger sample of the benchmarks, then we'll be able to anchor this model atmospheres over a large parameter space. So to do this kind of job, benchmark brown dwarfs are definitely excellent empirical anchors. So as I mentioned before, by benchmarks, I mean the brown dwarfs that are either companions to stars or members of young moving groups. So that means they're physically associated with stars. So they typically have pretty high mass, like over 10 or several 10 Jupiter masses. And they are widely separated from the stars that they are associated with a separation beyond several hundred AU. So given the mass and separation, these benchmark brown dwarfs are likely formed like stars by gravitational stability. So this means for these benchmark brown dwarfs, we can get their distances, ages, and compositions independently from the stars. So from the distance, we can get a sense of the TAF of the brown dwarf, because the distance tells us the volumetric luminosity, and then all of the brown dwarfs more or less have a 1 triplet radius, right? So we can get the TAF. And the age of the stars tell us information about the surface of gravity. And finally, the composition of the stars can tell us the metallicity and the C2 ratio of the brown dwarfs. So now basically we can see like for the benchmark brown dwarfs, if we directly observe their spectra, then this spectra basically can answer the previous question. Like they tell us how the spectra look like for a given combination of the TAF, log G, and metallicity. And our goal is to expand the census of the benchmark brown dwarfs. So in order to find more benchmarks, the large sky surveys are definitely extremely useful resources because they provide multi-band photometry and also proper motions. So technically, they tell us like over the entire area of the sky, or a large fraction of them, what are the colors of the sources and how fast they're moving. So based on the photometry and proper motions, then we'll be able to find some kind of co-moving pairs. And the smaller companions in the pair are hopefully brown dwarfs or brown dwarf mass objects. So for example, here on the left, I show an image from Pan stars. This is for a really small patch of the sky. And the red dot there is an L6 brown dwarf. And based on the proper motion highlighted by the arrows, we know it is co-moving with a young star. So we know this is a new benchmark brown dwarf. So in order to search for more brown dwarfs, we can take a look at all of some kind of significant resources in hand. So there's a list of kind of large surveys, including like Pan stars. So Pan star, as Will mentioned already, it provides optical data for 3/4 of the sky. And then UK's hemisphere survey, short for UHS. This provides the near-field data for the northern hemisphere. So Vista hemisphere survey is a counterpart of the UHS for the southern hemisphere. And also we have CatWise 2020, which covers the whole sky. So given all of these resources, I've been leading a program called Coconuts. The full name is Cool Companions and Ultrawide Orbits. So the goal of the program is really try to do a dedicated search for these kind of wide orbit brown dwarf mass companions. And hopefully we'll find some kind of companions with planetary mass. So to start with, we assemble a list of primary stars. So the list contains 300,000 stars from Gaia. So they have parallaxes and therefore distance, and also they have proper motions. Some kind of bright primary stars also have RVs. On the right, I show a sky map of our primary stars, and an important fraction of them are young stars. They're younger than 300 million years. And then we go to the most kind of tedious but important step, which is to identify the candidate companions. So basically, we combine the data from Pan stars, 2MASS, UK's, All-Wise, and in the later stage, CatWise was available, and we also make use of that. So in total, we have like 10 photometric bands, and also the proper motions, which is computed based on the long kind of baseline around and shorter than 15 years. And then we design a lot of photometric criteria, because the thing is like the whole database is really large. It's like a petabyte, and we want to bring it down into some kind of small manageable list of the candidates. So we want to be smart, and we want to try to design some really, really useful criteria. So one set of the criteria are based on photometry, so some cuts in the magnitudes and colors, the paper by Will, Bass, and collaborators, and also Ultracool Sheet has been really useful to let us know what are the typical colors and magnitudes for these brown dwarfs. On the right, I show an example criterion that was used to select some brown dwarf candidates. So basically, for all of the young objects, I mean, all of the candidates orbiting young stars, we try to find brown dwarfs with spectral types later than M6. And this kind of spectral type is indicated by the colors and magnitudes. And if they're old, like older than several hundred million years, then we'll try to find some brown dwarfs later than L4. So this kind of spectral type cut is try to make sure that the candidates companions that we found will be lower than the hydrogen burning limit. So basically the whole process sounds pretty straightforward, but it was really kind of non-trivial. And we basically reduced the database from the petabytes down to like a small list of 1 megabytes of the objects. And then the most exciting part of this is to confirm new companions. And to do this, we need to do some kind of follow-up observations, and we use several kind of telescopes. And this includes Euclid, CFHD, IRTF, Gemini. We want to make sure that these candidates that we found are really co-moving with the star, and they really have a spectra that tell them like they are ground dwarfs or planet mass objects. So the follow-up observation is equivalent to like 94 nights of the observing time. So it's really a huge kind of time investment for this. So here I list some kind of published discoveries from the COCONUS survey. First of that, we call it COCONUS 1, and it was composed of a T4 brown dwarf orbiting a really old white dwarf. And this kind of white dwarf, brown dwarf binaries was really were pretty rare. So we are really excited to find one more of that. The second example is COCONUS 2. The companion here has a spectral type of T9, so it's really cold, like 400K. It has a pretty low mass, and the whole system is located only at 10 parsec. So it's pretty close to us. The third example is COCONUS 3. The companion is like a young L6 dwarf orbiting a young M5. So beyond all of the 3 published discoveries, we have also made a gallery of all of the remaining discoveries. So in total, we have around 52 new companions, and we're now trying to publish all of these kind of new discoveries. And these results are basically telling us or demonstrate on the great potential of the large sky surveys for finding these interesting benchmarks. And to move forward, I think I'm really excited to see like what we can find in the era of the LSST. So here in the diagram, I show the estimated sensitivity of the companions that can be found from the COCONUS program and also some kind of a future survey. The diagram is in the mass versus effective temperature. So the blue area basically tells us the typical sensitivity of the COCONUS program at 70 parsec. So basically the boundary here represents the limiting magnitudes of wideband pan-star data and W2 of the all-whites. But then, like if we think about combining VHS, for example, J-band, with the wideband of the LSST, we'll be able to, so we need at least 2 bands to establish a color for spectral type estimation. So basically combining these two, we'll be able to see more companions towards new extremes. So some of these companions will be have cold temperatures, young ages, and low masses if they're there. And beyond 100 parsec, we can also try to find more companions in the slightly distant star-forming regions, which are even younger than the 100 parsec solar neighborhood. And this kind of red area highlights that we can probably find some kind of Jupiter mass companions. So I think overall, I'm pretty looking forward to some new discoveries to be made by the LSST. And I will just stop here and ready for a question.
Excellent. Thank you so much.
And can you explain this graph just a little bit better? I'm not really understanding it.
Oh, the diagram shown on the screen. So okay, so let's just see the diagram on the left. So the y is mass and effective temperature on the x-axis, and there are several solid lines, and these are kind of isochrones for different ages. And for the COCONUS, you can see the blue area. So basically the line at the bottom, that blue line basically marks the 10 million year boundary. So it's like in the solar neighborhood, we cannot find like stars younger than 10 million years. So that's basically the youngest age of the solar neighborhood that we can find. And then the like a vertical line, blue line here is basically like if we convert the wideband, the limiting magnitudes of the wideband of the pan-stars into the mass and the effective temperature. So, and this is based on the typical magnitudes of the Ultracool Dwarfs from the Ultracool sheet. So basically the nearly vertical blue line tell us what is based on the limited magnitude, what is the coolest and the lowest mass objects that we can find from the survey, from the pan-stars and all-white survey. And the red area is similar, but now we update the limited magnitude to use the value of the LSST Y band and also J band of the VHS.
Okay, thanks.
Bhavana?
Hi, ZJ, how are you?
Hi, how are you?
Doing well. So I have a question about the binaries. So the binaries that you select, you observe both the A and B component, right? Using the telescopes that you mentioned.
Yeah, so yes.
So in this, how do you have the confirmation rate? Like, how do you know that it is a brown roof? Apart from the colors, what is the confirmation rate of depending upon colors?
Oh, okay. So basically, I think, if I remember correctly, something like 80%, if not 90%.
Okay.
So it's like we have something like 10 to 15 or 20 different color cuts or magnet cuts. So it's pretty.
That's a
We
lot.
try, we try our best to make sure the candidates have a pretty good quality.
Okay. I don't know whether you know this, but there is another survey called as LAMO. It's a Chinese survey, LAMOST. So they also do an all-sky survey, but the advantage of that is each and every stars that they observe, they get a spectral type of each and every star. So it's easy for anyone to just observe the companion B in that case. And they have observed quite a lot of brown dwarf pairs. But their data is not public, so I guess we need some sort of collaboration in order to access the data. But yeah, I'm using that data to observe brown dwarf binaries, where I have like M6, but brown dwarf A, but I don't know what the companion B is. So right now I'm observing those targets.
Yeah, that sounds exciting.
Okay.
I think Will is next.
Yeah, hi ZJ.
Hi, Will, how are you?
Good, thanks. The plot that's still showing here, I'm curious where Catwise fits into this. Is it a limiting factor, or is like the coconuts limit, is that already incorporated there, or how would it contribute?
Yeah, so I would say cat-wise, if you can see my mouse, so it's basically, so it's you can think about making a line between connecting the top of the blue line here and the bottom of the red line here. So cat-wise is something like connecting these two dots. So I would say cat-wise can definitely make the coconuts deeper, but relatively, I think the VHS and LSST are pretty. Yeah, I would say like combining all of this will be really important. It's just like at the thinnest end or the coldest end. Seems like the J of the VHS and the Y band of the LSST is really pushing the boundary here.
Okay, great. Thank you.
I suppose as you go to larger distances, of course, the components get closer together on the sky. Is that a problem at 140 parsecs, or are you only would you lose half the coconuts discoveries, or only a few percent, or?
Yeah, I would say like basically for the coconuts, we mostly find companions with separations above 500 AU. So at 140 parsec, that means something like 4 arcsecond away. And I need to look into like the typical PSF size, but I would think like 4 arcsecond would be still fine. But the crowding in the young star forming region is definitely will be an issue, especially for raw Fucus. But probably still fine for the Scosen and the Taurus. Not Taurus for the LSST, but maybe Scosen. Yeah, some kind of young area of that. But this is a good point.
Wei Long. Say it right.
Hi,
Sorry.
Jake. This is Wei Long from University of Arizona. So also on this particular plot, so a quick question is, you just mentioned that with the deepening in the LSST, when actually pushing the discovery space a bit like further. My question is particularly on Euclid too, since Euclid Y-band is also on a similar depth. But do you think that including Euclid would actually give you any benefits on that?
Definitely, I would say Euclid have an estimated J-band limited magnitude of like a 23.01 or 09 magnitudes, I think. So that's something like 3 magnitudes deeper than VHS. So I would say like combining Euclid and LSST will definitely push the boundary toward the colder temperature. I did a calculation, something like the coldest TEF will be something like 650K, like combining LSST and Euclid. Yeah.
Great. And then also a following with actually Will questions too. So up to this case, if including SST and Euclid, does the limiting factors become wise for the matrix then? Because like Y is much shallower than both of them, and I think you need Ys to actually do careful color selections as well. Is that correct?
Yes, I think the more bands, the better. It's like for this kind of boundary, we usually only have one color. So that means a lot of like contamination, definitely. Yeah. So in that case, we'll have Y and J. So Y minus J color is still fine. It can help us to exclude some kind of earlier type stars, but as you said, yes, it will bring some contaminants.
Okay, great. Thank you.
In the spirit of encouraging discussion, and slipping on our timeline a little, maybe we'll go with Tom's question next.
Yeah, I wanted to ask the boring technical question of how you combined your data sets. I'm assuming you used nearest neighbor matching?
Yeah, so we used a tool made by Eugene Magnier at University of Hawaii IFA. So it's called EBO. It's a desktop virtual observatory. So basically, he has done a lot of work to cross-match different kind of data sets together.
Do you know the radius? Do you know the radius you used?
Yeah, I think. Let me see. I think 2MASS is something. 2MASS is 2 arcsecond. WISE is 5 arcsecond. Between 2MASS and pan-stars, and WISE and pan-stars like 5 arcsecond. So I also did some kind of research on the radius thing, and I think 2 and 5 look okay. Yeah.
Okay, cool. Thank you.
And I think Aaron is next, so maybe we'll move on to Aaron's talk.
Okay, let me try to share my screen. We know technical difficulties here. Can folks see my screen?
I see it.
And or hear me?
I see it and hear you.
Great. Yeah, so I think my talk might be a little bit of maybe a more niche and less scientifically mature version of Christian, so I think the order might pan out well here. I'm not going to be talking about the broader issue of ultracool dwarfs in the galaxy and in distant populations like the thick disk and halo, but more specifically about halo T dwarfs with Rubin and LSST. And this is very preliminary stuff. I ran a bunch of the numbers like last night, basically. It's a project I've wanted to work on for a couple years, but haven't gotten around to it as much as I would have liked. So I'd start off with a couple of remarks about why you might want to look for T dwarfs in the Milky Way halo. So one is that, kind of as Eduardo alluded to a couple of talks ago, we want to understand things like the mass function as a function of different parameters like age and metallicity in different galactic populations. And also to the extent that you believe we'll find giant planets that are around metal poor host stars, you might want to get an atmospheric preview of what happens to atmospheres in this temperature range, this low temperature range, from brown dwarfs where you don't have the interfering glare of a primary star. So yeah, as I said, this is kind of a relatively niche subtopic within the broader topic of galactic structure and galactic populations with ultracool dwarfs. So in this talk, I'm going to focus on something that we've nicknamed ESTTs, which stands for extreme T-type subdwarfs. Along the bottom, you can see the scale that's typically used in terms of mapping metallicity to these adjectives like ultra and extreme and so forth. So subdwarf typically means around a metallicity of minus 0.5 dex. Extreme subdwarf typically means a metallicity of -1 dex, and ultra subdwarf would mean metallicity of minus 1.5 dex in this jargon. So extreme T subdwarfs then are what happens when you get the combination of a metallicity of around -1 and an effective temperature of less than or roughly 1400 Kelvin. And so this is a very timely topic, I think, because it's only in the past few years that we've discovered what we think are the first potential or likely examples of these. What I'm showing here in the figures is a set of spectroscopic plots from a paper by Adam Schneider in 2020, where we had discoveries from Adam's previous NEOWISE search back in 2016, and also from the Backyard World Citizen Science Project that we had followed up and looked like they had really odd spectra, which don't match any of the standards. As you can see here, we tried T-dwarf standards, we tried subdwarf Ls, subdwarf Ts, and nothing really matches all that well. We also didn't get a very good match to models. These are some custom-made Phoenix models from Roman Gerasimov in Adam Burgasser's group at UCSD. And so based on a combination of kinematics and whatever indicators we can get out of these spectroscopic comparisons, which aren't exactly definitive, we think that these are the first known examples of what we call these ESTTs, so temperatures of 1400 Kelvin or lower and halo-like metallicity of less than or equal to -1. So the way that we've been doing this so far, and I'll get to how things change with LSST and Euclid in a couple slides, but the way we've been doing this so far is almost entirely based on WISE, where we have a combination of proper motion and color selection. We generally want to look for things that have high reduced proper motion, indicating they're relatively faint and fast moving in combination. But also we want to use whatever limited color information we have. And so this is the way that we've done it in practice, where we have, typically these are the two most readily available colors. So W1 minus W2, so you get one color from WISE, which is generally how we do the discovery and the proper motion to begin with. And then if we're lucky, we can get a deep J-band detection or a deep J-band limit. And so you can see that there's various populations of ultracool dwarfs, brown dwarfs on here, including normal T-type dwarfs and normal L dwarfs. And what we've been finding with WISE 1810, WISE 0414, the potential to extreme T-type subdwarfs, the first ones, and some other new candidates that we've had, is they're filling in this kind of middle ground of this color-color diagram that was previously empty. And so this has been our primary selection technique. And so far, we only have 2 spectra. We have a third spectrum, actually, that turned out not to be all that metal poor. That's 1553 labeled down there in the gray hatched. We have several more candidates that simply just don't have spectra in a lot of cases because they're very faint in J, to the point where you need something like maybe Magellan if you're lucky, or more likely HST to get a near-infrared spectrum. So the way we were doing this, it was actually empirical. We had just noticed this box in color space, but it turns out that after the fact, we had compared to some models, and the models kind of also agree, at least qualitatively, that as you go to lower metallicity, you can see there's the sequence of temperature series here. As you go to lower metallicity, you start to push up and to the left in this diagram into this previously unpopulated portion of the color space. So in a paper I published a couple years ago, there was this grid of models. It's more than 8,000 models, so it's quite extensive in terms of coverage of metallicity and temperature and so forth. And it was produced by Mike Line for us at Arizona State University. And so these low Z models I'll come back to, but they're very useful because it hasn't been especially common in the past to have really great coverage of the model grids into the low temperature plus low metallicity regime. So anyway, there's reason to expect that what we're selecting is what we thought we were selecting, and I'll also show some examples of this. Maybe we could do it the other way around for LSST, where we actually figure out what we should look for before the data comes, because we still have a chance to do that. I did also want to mention one other object from this plot. You might have noticed right near the very top, it almost goes off the plot. We nicknamed it the accident. The nickname comes from its discoverer, Dan Castleton, a citizen scientist who was on the call, at least recently. He may still be on the call now. I just wanted to throw this in the mix because we don't actually know whether this is a T subdwarf, or it might be a Y-type subdwarf. We think the temperature is between 400 and 550 Kelvin. And we probably don't know how to even define the TY boundary at low metallicity anyway. But this is a really interesting object, very high proper motion of 2.7 arc seconds per year, trigonometric parallax, placing it at only 16 parsecs, with a tangential velocity of 205 kilometers per second. So it's kind of remarkable to have something moving that fast, that close to us. Its kinematics imply that it's in the halo basically for any radial velocity. And this will be observed with JWST during cycle 2. It's an approved target now. And the plot on the right is from a paper by Davy Kirkpatrick, just showing that this object is really weird. It's an outlier by many, many mags, maybe not quite 10 mags, but getting there in this color magnitude diagram. So I think this is part of the Halo T-dwarf story. Is it may be a very broad swath of parameter space observationally that these things span, although I think with LSST and Euclid, we'll primarily be targeting the warmer T halo dwarfs. So one area that I think is really ripe for further investigation is the red optical colors of these extreme T-type subdwarfs, because very little work has been done so far, and I think there's still some more data out there that could be looked at. So this is basically all the data we have so far, mostly from the IAC group in these couple papers by Zhang and Ledoux in recent years. So I basically took those colors that I tabulated there from the Ledoux and Zhang papers, and I made a very crude forecast of what I think will be the distance limits for these extreme T-type subdwarfs in LSST and also Euclid J-band. So the Y's distant limit for reference is 55 parsecs, scaling from Y's 1810. The reason I scale from that one is because it's the only one of the two that has a good parallax. The other one could use a parallax. Then, so from the LSST key numbers page, they list the co-added depths after 10 years in each band in AB magnitudes, and then you can convert that to a limiting distance. So I band is 30 parsecs, not the best band, just because you're going a little too blue. Z band gets to 85 parsecs in LSST, and Y band gets to 130 parsecs in LSST. Interestingly, I got a very similar number for the distance limit in Euclid wide J band of also about 130 parsecs. So it appears that for this particular population, Euclid J band from the wide survey and LSST Y band from wide fast deep are actually quite well matched. The other thing I thought would be interesting to do is to figure out, okay, given this distance limit, if you had a halo-ish tangential velocity of 100 kilometers per second, what does that translate to in terms of a proper motion? So that's a total motion of about 160 milliarc seconds per year, which I certainly think should be easily detectable with LSST, and that raises questions about also the astrometric combination of, say, Euclid and LSST for proper motions for a longer time baseline, at least early in the LSST survey. Yeah, so these last numbers, they turned out to be a little less impressive than I was hoping for, but LSST and Euclid each give something like a 6.5 to 5 times volume enhancement relative to what we can do with Ys, but of course those volumes aren't entirely overlapping. So combined, it's something like not quite 10, but more like a factor of 9 times volume enhancement. So maybe we can go from a handful to 50 or so. Yeah, so this is very preliminary work, but as I showed in that other figure in color space for the infrared colors, you could also try to do the same thing with the same low-Z models that span a lot of parameter space and ask in LSST-like filters, what do you see there as far as the changes in the colors as a function of metallicity and temperature? And so here's just kind of a toy example I did, running a set of temperature sequences, running from metallicity of 0 all the way down to metallicity of minus 1.5. And then this is actually in the DCAM system, but okay, it's kind of similar to LSST a little bit at least. And I would say that there's clearly some difference in the behavior of the colors here as a function of temperature. What is less clear, and I think would be an important next step in this project, is to actually overlay this on other populations of point sources or nearly point-like sources to understand, you know, just because two different ultracool dwarfs look different from each other doesn't mean you can distinguish them from the much more numerous background population. So that, I think, is an area that would be really interesting to explore further, and possibly Christian already has much more than I have. I did have this slide in here before I saw Davy's talk. It's very similar to a slide that Davy had in his talk. So there's this project called Backyard Worlds that has demonstrated the efficacy of color and motion brown dwarf searches, leveraging a crowdsourced approach, so citizen science, as it's sometimes called, or participatory science. This is also particularly relevant for Rubin because Rubin is building a convenient pipeline for uploading LSST data to Zooniverse. So I think this presents a real opportunity to build on Ultracool Dwarf citizen science with Rubin, whether it's through motion detection by eye or color or both. So yeah, this is, as I said, very preliminary work. The remaining major questions that I would hope I get to or somebody gets to before LSST starts is how do model predicted LSST colors of ESDTs compare to colors of other nearly point-like populations that LSST will see in much larger numbers? What is the relative importance of color versus motion selection in LSST? With WISE in the early days, there was a lot of color selection, but over time, the focus has shifted more to motion selection. So I'll be interested to see which turns out to sort of be more valuable with LSST. And then I haven't worked out any of the details of exactly how I would want to combine Euclid and LSST for these types of searches, but I suspect given that some of the detection limits are similar for these types of objects, there's a lot of room to do that. So I'll end there. Thank you.
I mean, I suppose one of the advantages of the proper motions is you don't prejudge that the models are correct, right? I mean, although I guess you already have evidence that, qualitative, that at least in part they are correct. But, if something's moving at 0.1 arc seconds a year,
Yeah, that's certainly
that's worth looking at.
That certainly whittles down the parameter space, right? One thing you could do is, okay, I'm going to select only point sources. But, what would get you a lot further than that is point sources that have distinguishable proper motion. So I agree with that.
Cool. Adam has his hand up, so maybe we'll.
Yeah, thanks for the talk, Aaron. So you report the co-added LSST sensitivities, but for these things that are moving quite fast, and this is maybe a general question for folks who are more engaged with the LSST plans. If something's moving that fast, it doesn't necessarily show up in the co-added data unless you're purposely offsetting for proper motion. So what are the equivalent single epoch limits? And at that point, do you win over WISE, or is it just now more information in addition to WISE to kind of narrow down the selection?
Yeah, I'm not fast enough to do that off the top of my head with the conversion from magnitudes and so forth. I think I'll refrain. But you can certainly imagine data analysis approaches that are able to reach close to the co-added depth, even for objects that are moving of order 1 PSF size over the course of the survey. One example that comes to mind is the tractor, which is written by Dustin Lang, which is kind of a forward joint modeling of all of the individual exposures. So if you had a version of that had linear motion as a free parameter, you could do that. Maybe you would need to combine that with sort of setting the detection threshold a little bit below 5 sigma in the initial detection step in order to avoid missing these objects before they even get into the proper motion fitting. But also the AllWise and CatWise pipeline also did a thing called motion aware source measurement. So it doesn't seem, 5 or 10 years from now, it doesn't seem out of the realm of data analysis possibility that you could do a good job of this. But I also agree that I did have this, asterisk here about assuming you actually can reach the full co-added depth. And I'll do the homework assignment of figuring out whether the single epochs actually buy you anything compared to WISE or other stuff.
Yeah, I mean, I can imagine if you knew the motion ahead of time, this would work. But if you're just, things have arbitrary velocity vectors, it's a little harder to build a sample that way.
Yeah, but I still feel like if you just turn the detection threshold on your static sky coad down a little bit beyond 5 sigma, and then you run one of these motion aware fitting codes like the AllWise software, for example, you should pretty much get close to the nominal co-added depth, I would think. But you could also do some things like what we've done with WISE of like co-add in yearly intervals or something. So I really don't, my sense is that the detection limit for these things will definitely not be very close to the single exposure. I think it'll get at least partway to the co-add depth, if not very, very close to it.
Thanks.
And Dan had a comment. I don't know if you want to make it out loud or I should repeat it from the chat.
Sure. I was just saying another option is those neural networks that can do source detection on stacks of images natively.
Yeah, that's a great point. I don't know about the scalability of that approach to the LSST data volume, but yeah, Dan has done some pioneering work combining machine learning with motion detection in the low signal regime, and it's helped find some of our best, or a lot of our best moving object candidates from backyard worlds. So I wouldn't count that out, especially given how fast things seem to be developing with GPUs and AI and so forth.
Well, maybe we'll move to Christian's talk then.
Yes, let me share my screen. Can you see my screen?
Yes,
yeah.
we can.
Yeah, thank you for having me here, and thank you for staying for the last talk of the meeting, at least for this session. My name is Christian Aganze. I'm a science fellow, or also Rubin fellow at Stanford. And today I'm going to be talking about basically making the case for doing galactic archaeology with brown dwarfs in the era of Rubin. And in the end, I will present some preliminary simulations showing the expected counts and possible selection criteria for brown dwarfs in this survey. So I'm just going to start with a nice picture of the Milky Way. That's what galactic archaeology is about. It's about exploring all these structures in the Milky Way and studying them by using stars. So here's a nice picture from Gaia. This is a star count map of all the stars in the Milky Way. I think they have, at least that they could detect around 1 billion stars. And in the middle, you can see the galactic disk, and then you have a lot of extinction. And then some of the structures like the LMC and SMC can be seen there in the lower right corner. The Milky Way is mostly broken into this, at least the classic picture is you have these components that are in equilibrium and possibly of distinct origin. So you have, we live in this thin disk population, which is shown here by this ellipse here, which is mostly metal rich and relatively young compared to the thick disk, which is more extended and kinematically heated. And then this thing lives inside the Milky Way halo, which is a much older population. And inside the Milky Way halo, we see globular clusters, and we have dwarf galaxies that are orbiting the Milky Way potential. And this entire structure lives inside the dark matter halo. And we know a lot about these populations from, for instance, if you look at SDSS, we're able to do star count maps and map like the structure of the thin disk, for instance. So here's an image of that. So this is a 2D map of the stars in SDSS. This is from Zurich et al. 2008. This is R versus Z. This is galactocentric. So the galaxy center is at 0 in R and Z. And then this is color-coded by the log density. So we see this exponential decline in the number of stars as you move far away from the Milky Way disk. And then you can also have that plotted in one dimension. So this is one-dimensional density versus galactic height. And this can be fitted to a very nice power exponential with one parameter, which is called the scale height. And then the Milky Way disk source lives in this scale height of around 200, 350 parsec. And then the thick disk is a little bit more extended, so around 900 parsec in scale height. And then there's in the third component, which is a spherical halo. And this is not an exponential, but it can also drop off as you go to high distances. So this is something we can learn from just looking at number counts. And we hope with LSST, we can do this kind of experiment with low mass stars and brown dwarfs and see if we actually get the same result. And we know a lot about the kinematics of the Milky Way by looking at, for instance, with Gaia, we have this new revelation that the Milky Way halo is really full of substructure. So here I'm showing the velocity distribution of stars in the Milky Way. This is from the Helmy review paper, which is actually taken from the Koppelman et al. I think the RVs are from apogee spectra, I believe, in this study. But they have, so the Milky Way disk lives in this ellipsoid around 200 kilometers per second. And then we have this thick disk, which is around above this ellipsoid that is shown here in yellow. And then what Aaron was talking about and other people want to talk about is LSST will be able to detect halo stars, which live in this structure here called the Guy-Enceladus blob. So the Guy-Enceladus blob is really the biggest part, at least, of the Milky Way halo, which we believe was a galaxy that merged into the Milky Way halo around 10 gigayears ago and deposited a lot of debris. And stars in the Milky Way halo tend to live on different orbits that are more retrograde compared to the galactic rotation. And then we can go further and look into the metallicity distribution, which we hope we can do with brown dwarfs, but we probably need really good spectra. Or later in the talk, I'll show some work with photometric metallicity work with K and M dwarfs. But in general, we know that we also get these clues about the formation and the evolution of the Milky Way by studying also the abundance patterns. So this is metallicity in Fe versus magnesium. And then this is color-coded by eccentricity, and it's taken from Michael et al. 2019. Again, this is, we're only able to do this kind of work thanks to Gaia. So the eccentricity is the eccentricity of the orbit in the galaxy. The main takeaway is that this heated disk population and halo population have a different chemical imprint, which also support the idea that the thick disk and the halo actually form differently from what we see in the Milky Way disk. So why should we use brown dwarfs to actually, since we know so much about the Milky Way from studying just FGK stars, why should we bother with brown dwarfs? So again, this plot here, a lot of you are very familiar with this. So this is an evolutionary model from Burroughs, this one taken from Burroughs et al. 2001. And it's showing something that we don't actually see in FGK stars. Is this cooling and evolution of brown dwarfs give us a time scale that can be exploited to age date different structures in the Milky Way, like the galactic halo, for instance, or globular clusters. So this is just an evolutionary model. You have age versus temperature, and then the color code here is mass. So we have different mass beams. So like the stars we just contracted the main sequences at the same temperature versus brown dwarfs that cool down with time. And this, again, we can explore this cooling to actually age the different clusters. For instance, if you look at the Milky Way, so this is a simulation that I run. It's a Monte Carlo simulation. So we take the we sample from the IMF, and then we evolve this with time. So if you look at the distribution of temperatures that you get for, let's say, a Milky Way disk population, which is shown in white, versus the Milky Way halo population, which is shown here. So disk is shown in blue, and then Milky Way halo is shown in red. You see a different basically histogram because things are cooling down to lower temperatures. And then there's a gap between stars and brown dwarfs, which can actually help us, at least for the Milky Way halo, have a better constraint. So you can imagine if you have a large sample of, let's say, Guy-Enceladus stars in LSST, for instance, we can run these models forward and try to predict basically the age of formation for that structure. So this, for example, this was for the halo, but I can also show some work by Raymond Gerasimov for different global clusters in the Milky Way. So this is for 47 Tuc, and this is just instead of a temperature distribution, this is showing a magnitude distribution. This is the number of stars. I think it's arbitrary. It's not actually the number of stars that detecting in the survey. But you see the evolution of stars versus brown dwarfs. So brown dwarfs are cooling down towards, so this is evolving with time. So brown dwarfs are cooling down, so you get this bump toward lower, fainter stars or lower temperature objects. And then the gap between brown dwarfs and stars kind of gives you the age of the cluster. And we can do this because we know that brown dwarfs are extremely common. So this you heard about this from David's talk, but we have the recent constraints on the mass function, which shows that you get you have way more low mass stars than high mass stars, also including brown dwarfs. So you get this trend here. So this is just showing that those results. This is mass versus number of objects, and this is different fits. So what can you do with large samples? For instance, what I meant to say, what I talked about in the beginning, is that we can actually do the same kind of work that people did with FGK stars by looking at low mass stars and brown dwarfs. This is a work by Kim and Lepin 2023, where they're showing the velocity distribution of nearby, actually not nearby, this includes the object of a KPC. So they have 500,000 objects, but this includes 200,000 KNM dwarfs that extend up to like a KPC. So these are projected velocities, so they don't have RVs, but they were also able to get photometric metallicities by training some kind of a machine learning algorithm. So you can imagine doing the same kind of work where you can actually recover. So the structure that you see here is most of these stars are Guy-insulated stars. And then you have the ellipsoid at the center that's shown with the yellow star. That's the thin disk. And then there's a thick disk population as well. And then with distance samples, so this is maybe not LSST, but this is probably talking about the work that you saw from Eduardo talk, where we're talking about Euclid. Euclid will be able to detect objects that are at tens of KPC or KPCs for T-dwarfs. What I'm showing here is just my work on HST. So we have this sample of 164 mLNT with like less than 50 LNT, but these objects extend to a KPC in galactic height. So this is galactic radius versus galactic height. And each color code here is just a different spectrotype range. So we have M, L, and T dwarfs. But you can imagine kind of combining brown dwarfs in Euclid and LSST and JWST to actually have this large sample of distant brown dwarfs. What can you do with distant brown dwarfs? So you can do something like constrain the scale height. And when we're constraining the scale height, we're really trying to map the galactic dynamic coherent history of these objects that you heard about from, I think, Wilbe's talk. So what I'm plotting here is type versus scale height. So the E-folding scale, so after one scale height, you get a density drop-off of 1/E. But this is scale heights versus spectrotypes. So white is what they had in the literature versus what we measured from this HST study. And what was shown in this study was that the scale height decreases when you go to the L dwarf regime, at least the L dwarf regime, because the L dwarf population is a much younger population. So scale height really correlates with the vertical velocity dispersion, and then it also correlates with the population age. So L dwarf as a population is a young leaf phase of brown dwarf evolution. So you expect that to be to have a small velocity dispersion, which have been shown. If you look at, for instance, some work by Dino Su and Adam Bergasta and Jackie Ferretti and others, they've measured the velocity dispersion of local brown dwarfs. But this is actually going further into the, so we can actually measure the scale height. And we see this consistency that L dwarfs are generally a younger population. But in this study, our initial assumption was starting with a uniform age distribution, and then we try to actually which if you looked at Wilbe's talk, is probably not a good starting point. But upcoming surveys, since I have like 3 minutes, I'm going to talk about upcoming surveys, talk a little about LSST and what it's going to do for us in this realm. And I'm going to try to compare LSST with other surveys. For instance, we know we heard about Euclid, which is launched in July. Rubin Observatory is next, and then we're going to have also the Next Instrument telescope. What I'm showing here is the log area of a survey versus the distance you can see at L dwarfs too. I have some JWST surveys here, so like surveys that go to like 27 versus like 29 magnitude in J. And then yellow here just means that the survey is upcoming. You see that with Rubin, Roman, and Euclid, we actually getting like an order of magnitude increase in the distance we can probe these objects to. If you ignore JWC, because this field is, if you're just talking about wide field surveys. So what I want to show is some predictions for the number of objects we expect to see in LSST. This is going to be using some Monte Carlo simulation framework. So we start with some mass function. You assume some star formation history, and then we add all these other inputs, and then we just for model that, and we predict that the counts, the type distribution, the magnitude distribution, the distance distribution, and so forth. So these are probably the inputs. I'm showing some of the inputs here. So you have like you're sampling from some kind of galactic structure model, so an exponential disk and a spherical halo. We've just choose a few set lines. You don't. It's very hard to simulate the full galaxy with this kind of framework. Then you input some kinematics. So we have some. We assume just that the Milky Way disk is some kind of ellipsoid, and so same thing for the halo and the thick disk. But you can imagine that if you actually want to have a dynamically motivated model, you can also include that in here. And we have some age distribution that follows. In this case, we're just using age distribution that uniform for the Milky Way disk and halo, and some kind of age velocity dispersion relations for the Milky Way thin disk. And then, so my predictions here are shown here. So here we have type versus number of stars you expect in the Rubin 10-year survey. So this is the solid line is the thin disk, the dashed line is the thick disk, and then the points are the halo. We expect to see maybe hundreds of thousands of halo stars weighted towards the colder objects. And then we expect to see millions of thin disk objects if we look into the full footprint and the full 10-year survey. And this actually include constraints that we actually, we have this parallaxes and this proper motion precision. I also have some predictions for, this is just convolving models with photometric filters. This is how we select them. So this is R minus C versus G minus R, for instance. And each point here, just those models, and the models are from Roman Gerasimov. I think they're also on his website. You can go download them. And then the dark points here are the DP0 data, which you heard about in Federica talk. This is a simulation from the dark energy survey, but they have stars in there. So these are the stars in that survey. And then, so we should be able to select this object by probably drawing some, this is probably one selection. This could be another one if you have this magnitude and so forth. So you can imagine doing the different kind of colors where, or combining different colors and selecting these objects. But optimally, probably using machine learning would be the best thing to do for this kind of multi-band photometry selection, because you probably have a lot of background. So here I'm only showing stars, but you could imagine some red, let's say quasars or other contaminants that I didn't include in this simulation. But you should definitely be able to select this object and probably able to spectralize them by colors if you use some kind of sophisticated machine learning framework. So you can also imagine doing some kind of purple motion selection. This is preliminary. Again, I'm doing like, this is if you simulate the entire survey, and then this is within the magnitude limit of LSST, but you then you impose the purple motion selection and the parallax selection. You might miss a large fraction of the, so a lot of objects that are visible in LSST will not have detectable motions. So I'm going to leave you with the summary here, since I'm 2 minutes past. So the case here is that low mass stars and brown dwarfs are excellent traces for the structure of the Milky Way because they're so common. And since you have so many stars, you can do great phase space resolution of different structures in the Milky Way. And then you can explore this, the metallicity and ages to actually constrain ages of different classes in the Milky Way. In substructure in the halo, in the disk. And then we think Rubin will detect millions of thin disk objects, tens of thousands of thick disk and thousands of halo sources. And then if you combine this with Euclid, Roman, and I think, HST and all those archival data, you might be able to actually we get like millions of objects, and this would be a huge deal, at least in the brown dwarf community. Hopefully, we're all ready to use this data to actually start using these brown dwarf star stresses for the structures of the Milky Way. Thank you.
Excellent. So now it's time to move to questions. As you can see in the Slack, Will, speaking probably for many of us, says, I love these structure simulations, going to be helpful. Adam?
Well, I'll help stimulate the conversation. Christian, what are the main things you're missing right now in the simulation that, we as a community need to be measuring or modeling in order to really do these simulations in a reliable way?
Yeah, the question is, what are we missing in the simulations?